our expert, Mr. Simranjit Singh Chabra. He is working as embedded system design engineer at SGS Electronics Mohali. He has of kernel in real-time operating system. Then how these real-time in real-time embedded applications like in automobile industry. So using number of buses like CAN bus and with the help of I2C buses, he will show us that how these DRES systems, that is distributed real-time embedded systems, are useful in our day-to-day life. So with these words, I welcome Mr. Simran in our studio and request you to kindly proceed for the session.
Good morning to everybody, and thank you very much, Kanika ma'am, for the heartily welcome. Today we'll be discussing on the topic that is the distributed real-time operating systems, embedded system also. And before starting with the actual topic, I'll like to introduce myself. That as ma'am has already said, that I am an embedded system engineer at SGS Electronics. My area of work basically pertains to the embedded systems, and also I have a very keen interest in different softwares starting from the MATLAB and VLSI, and also have worked on PLCs. So I'll try to encompass all the experience and try to give in as much as I can give you on the topic distributed embedded real-time embedded systems. Now, starting with the topic, the first thing that comes to us is that what basically a distributed real-time embedded system is. Distributed real-time embedded system is not a single term that has evolved suddenly out of nowhere. It has evolved because of continuous process that has been followed. That initially, in case if we say that generally we know that it is said that necessity is the mother of invention. So when initially we didn't have any of the tools, the fire was invented with the help of stone. And after the development of fire, we made sufficient tools available for us so that we can manipulate things and do in accordance with whatever we want. So this process, the distributed real-time embedded system, has been a chain of events which has led to its development. And that chain of events is basically, we can say, divided into three parts. Starting from the distributed embedded system, have the real-time system development, and after that we had the development of the distributed real-time embedded systems. Now moving on, so we'll be considering the entire entity into three different parts. The first will be the embedded system. Then we'll be moving on to the real-time embedded system discussion, wherein we'll discuss the different parameters of the real-time embedded systems and what are the softwares available for us to in order to realize the real-time embedded systems. And ultimately we'll be reaching on to the distributed embedded systems, and then how it is being used in the distributed real-time embedded concept. Right? Moving on, as we have already discussed, that initially evolution has taken place, and that evolution, we can say that initially this is the initial computer size. It took about the entire room, and these were the computers that were based on vacuum tubes. So these computers, and it is not that they, at that time when they were invented in 1945, they were considered to be very much advanced. Why they were considered to be advanced? Because at that very point of time there were no semiconductor devices, so we could not realize how to add to any of the two things, and these vacuum tubes basically had the inherent property of acting like a semiconductor switch. So that's why we didn't have the semiconductor devices, so we had to realize it with the help of vacuum tubes. Later on, as we moved on, semiconductors were invented, transistors got invented, and in that scenario, the size of the vacuum tube that was very large in its occupation reduced to a minor. And this is the size evolution process showing that how the size of the device has been actually starting to go down and down and down, and presently we have a very miniature size transistor available to us that is not even the size of a we can say the cube of sugar. So we have reduced the size to such a minimum level, and that process has been followed with the help of necessity. We found that initially we had very big handsets. We need to reduce its size. So we continuously did the research on that topic, and we were able to attain the size very small and ultimately reduce the size of our device. In a similar fashion, the distributed real-time embedded system has evolved over time, and that evolution has led us to the real-time systems. Now, starting with the embedded systems, we'll be first covering up the embedded system part, that what basically an embedded system is. We can say that embedded system is a system that comprises of a hardware, a software, and is a sub part of a larger whole. And in a layman sense, generally it is considered that embedded is something that is the combination of the hardware and the software. But that is totally in the layman sense. Why we say that that is in the layman sense? Because embedded system is a system that was designed with the key aim of sufficing a particular task. Means it was designed in order to realize a specific task only. In case I have a temperature monitoring system, in that sense, it will only sense the temperature of the room. It will not do any of the mathematical calculations. It will not do any of the other tasks. That is why that system, we started to refer to it as the embedded system. So from here, one thing that delineates it from the general purpose computer is that embedded system will always perform a specific task only. In case that task might include 2 or 3 purposes also, for example, temperature monitoring or detecting what is the humidity of the room or the atmosphere, that is an embedded task. But in case I have a device that is capable of performing mathematical calculations also, sensing the temperature also, then playing the videos and all those tasks, then that system, we cannot refer to it as the embedded system, because the definition of embedded states that it is used to provide a certain specific task only. That's why the general purpose computers or the laptops that we generally use are not referred to as the embedded systems, though they are a part of the electronic system, the larger electronic system, but they are not referred to as the embedded system, because they are not performing a specific task, they are performing a range of tasks, they are multitasking. Now, these are some of the examples of the embedded systems wherein we have the ARM controller board, the Arduino board. We'll be covering this topic tomorrow also, the Arduino controller, and the LCD display system. Why I have included the LCD display system in this example is because generally we can say that LCD is just a display. It doesn't perform any of the functions. But the LCD system is not a display system only, because whatever information is being displayed on the LCD is in the form of ASCII code, and that ASCII code is not cannot be understood by the LCD alone. Means whatever data the controller will be giving into the LCD has to be interpreted, and that interpretation takes place with the help of a controller. So what we have is, we have a controller and the LCD system, and the LCD system has an inherent controller in it that will understand the SI code that is being sent to it, and that's why it is referred to as an embedded system over here, because it is linked with a particular task of performing the decoding of the SI code that is coming, so that it can display the data on the screen. Then we have certain applications of the embedded systems. These basically these are a very few applications of embedded system, but we have immense and diverse applications of embedded systems, and they have occupied almost each and every field of the human life. The laser thermometer means without even touching the actual object, you can measure the temperature of that device or any of the object. And then we have the flow meters. This is one of the very critical and very creative thing that has been invented, wherein it can measure the amount of flow of the fluid within a pipe. And this has a very important application also. Why we are saying very important application? Because when we talk of the different industrial parameters, like if we take the petroleum industry, or if we take the recycling industry, or if we take any of the chemical related industries or pharmaceutical industries, all of these industries require fluids for the manufacturing of the devices or manufacturing of any of the products. For that sake, take the FMCG sectors, all the soaps or any of the household items that we are using, or any of the detergents or any of those sort of things are made with the help of leakage only. So that liquids are going to flow from one point to the other within the industrial setup, and that flow has to be maintained, that how much of the liquid is flowing, so that the same amount can be fed into the product that we are assembling. So these flow meters play a very important role, and we'll see in the coming video that what basically is the basic principle of operation of this embedded system. And then we have the hoverboards that basically run on the solar panels, battery charged they are, and they can automatically balance. They are basically based on the inverted pendulum principle. That inverted pendulum is basically based on a PID controller, wherein it can automatically adjust its position depending upon where it is going, and correspondingly generate a control signal that will enable it to balance itself as soon as possible. So that in that case, basically we are considering the PID controller, and that PID controller basically stands for the proportional, integral, and derivative controller. That itself is another topic that of discussion, but we'll not include it over here. This is a video showing the applications of the embedded system. Sound नहीं आ रहा.
सर आपके लैपटॉप के
So, after going through this video, we can realize, or we can visualize that in what sense the embedded system can play a part in order to realize the objectives that we require. Otherwise, the flow through a particular pipe is very difficult to determine. But with the help of just the embedded system that was determining it with the help of induced EMF, we were able to decipher what was the flow without actually interfering inside the liquid or interfering with the pipe structure at all. So these principles basically propel us to study the embedded systems in a very greater detail also. And that has led to the study of the real-time embedded systems. That we'll be covering up that what basically a real-time embedded system is now. Now, till now, we have been discussing just what the embedded systems are and how they can be used in order to attain a specific result. But real-time embedded system or the real-time systems are a part of the embedded system itself that have a very fixed or a bounded response that will give you now embedded system. No doubt we if we talk of any of the circuits that we want to develop, the first and the foremost task is that we need something from that system, and that need is always time bound. For example, if I devise a thermometer, that thermometer I want that whenever I analyze it, it should give me the correct result, and that thing is already time bound. That means in case I am visiting the thermometer device on a daily basis, then I need the response from the thermometer device on a daily basis itself, and I'll already make the device such that it can respond to me within 24 hours time. So that has already made the embedded system a time bound system. So in reality, whatever circuit that we are considering, or whatever circuit that we are assembling, has to have a time bound response, and that can be considered as a real time system itself, because there is no system that we can say that I'll just make up and the response of the system cannot be determined, or I do not require the response of the system. In case I do not require the response of the system, then it means that the circuit does not play a part in my specific role, that it doesn't have any role to play. So that system is of no use to me already. So any of the system that is of use to me has to be time bound to me itself. That's why we generally classify the real-time systems as time-bound, and they are a part of embedded system only. They cannot be differentiated from the embedded systems. And apart from being time-bound, it has to be logically correct also. It is not that I am giving the result in a specified time, but the result is wrong. That has to be correct also, and that has to be time bound also. So these are the conditions of a real time system, that it has to give the result in a specified time and the correct logical result rather than giving the wrong logical result. And based on this we have the classifications of the real time systems also. But at this point we'll be discussing that what a real time system is from the practical aspect. Till now we were discussing about the theoretical aspect, that what the theory says, but in reality when we talk of the real time systems, then we have to move away from the abstraction part, and we have to consider the uh, actual practical scenario that really exists. And the practical scenario says that it is a real time system is nothing but a change of the perception of a system's working. For example, when we talk of programming, the basic fundamental of the programming is to obtain a certain goal. Now that goal can be achieved with the help of procedure oriented programming also. That goal can be achieved with the help of object oriented programming also. But if we are achieving the same goal but with different methodologies, then what's the difference between using any one of them? The thing is, procedure oriented programming is suitable for very small or limited range of functions. In case the complexity of a program increases, then we need to shift our focus onto the object oriented programming, though we are achieving the same goal. The addition can be performed with the help of procedure and object oriented programming also, but the same addition when performed with the help of object oriented programming gives us a more linkage with the real world thing, because everything that we consider is an object. A chair is an object. An object of what? A class, I can say furniture. So but in a procedure oriented programming, chair is nothing but a function that has to be executed. But whereas in object oriented programming, with the help of classes, I can easily realize a chair also, a table also, anything else also. I do not have to write the code again and again because I have the main parent class. Whereas in procedure oriented programming, all the things have to be defined separately and they will be just execution of different functions. So that is basically a different perception. Though the process is not changed, the task is starting from 0 point, going till the end point, and that starting and end point are being followed by different routes. Similarly, for the real-time systems, the perception differs. And that visual perception is that we have been programming the embedded systems initially also with the help of different languages, C, embedded C also. Then we initially we had the Fortran, and in all the other languages starting from the basic also, COBOL also. So, but what was the difference between a real-time system perspective and an general embedded system perspective was that an embedded system was dealing with the execution of tasks only. But a real-time system we are considering has to deliver us the execution of the task within a specified time. So in terms of a real-time embedded system, the time will be independent parameter. Why I am saying the time will be independent parameter? Because the embedded system is going to respond in respect to the clock ticking. Each of the clock pulse that comes into the system has to decide, has to administer that each and every task that was supposed to finish at a specific amount of time has finished up. Whereas in terms of a normal embedded system that was not real time, we could say that it is basically concerned with the execution of a specific function. It was not concerned that whether that function will execute in a specified amount of time. That thing can take a number of cycles also. For example, we have the instruction set of 8051 controller or any of the other controllers. So there are one bit instructions, there are 2-bit instructions, and there are 3-byte instructions. All those instructions execute at a specified amount of time, right? But when we talk of the RISC and CISC architecture, the variation comes itself over there. CISC is basically complex instruction set computing, and RISC is reduced instruction set computing. The difference lies in the fact that in CISC architecture, each and everything is predefined. That if I have to go in from one place to the other, the route will be predefined. So each and every execution instruction will be predefined. But in RISC architecture, what we have delineated ourselves is that in RISC architecture, we have reduced the amount of instructions that we have to feed into the processor to move in from one point to the other. What we have given is the leverage to the CPU to, in order to move from one point to the other, and say to it that in case you are not being able to reach to that location from one particular route, you have the leverage in order to move on from a different route. So it is in RISC architecture that the CPU has the sole administration, that it can take its own path. Whereas in terms of a CISC architecture, complex instruction set, I have to give each and every instruction to the CPU that from this point to the other point you will be moving in this specified fashion that increases the overhead of the entire system. Means for every instruction I'll have to give the timing and the clock signal, and for that timing and the clock signal, what is the amount of the duration for which the task will execute, that also has to be provided. Like parity checking will also be done, and all frame error checking. So all those things increase the overhead and increase the delay of the system. That is basically what is referred to as the CISC architecture, and basically is the RISC architecture. Now initially I was saying that RISC architecture is basically its own administrator. It can decide its own route. So in case it can decide its own route, it is but obvious that the number of instructions that will be used for execution can vary. It will not be constant every time. It will vary, and that variation is what is not a part of the real-time system. We cannot tolerate that variation in a real-time system. So that variation has to be nullified, and that is included in the real-time system, and that's the visual perception. That one thing is just doing the task, taking whatever amount of time it takes to complete the task in order to obtain the result. The other thing is the clock is ticking, and you are always observing the clock and then doing your task, that I have to complete this task in this amount of time, next this amount of time. So these things will be these things are basically the foundation of a real-time embedded system, that you have to be time bound, and that thing basically can be classified into a number of ways. We'll be moving on and discussing those things also. But before we move on, we'll just consider that what are the terminologies linked with the real-time systems. The first thing is an instant. Now, instant is basically a slice of time or a specific point of time that we are discussing. For example, we have 10 seconds, and at the time instant of 5 seconds, I want to analyze what the parameters were. So that instant or that particular value out of the entire time slice that I have is referred to as the instant. And the event is the occurrence of a specific incident or any of the happening on the specific instant is referred to as the event. Event information is basically linked to what were the parameters of that event. For example, if I want to consider what was the temperature and atmospheric values at a particular event and in a particular instant of time, that values of temperature and pressure or the humidity will be the event information. Duration is basically the distance between any of the two instants in time, starting from one event ending on the other event. What was the entire duration of that event, right? And the clock tick, this is the main and the most important part of a real-time embedded system.
अभी नहीं आई हुआ 11 बजे आओ नहीं 11 बजे कितने हो गए 10 मिनट पहुंचे
Yeah, thank you.
और क्या मंगाना है? Green sandwich.
Now, the clock tick is basically the most important part of a real-time embedded system, wherein each of the event on the clock is referred to as an instant, wherein the system has to check that has it achieved its goal in that specified amount of time or not. Then we have the man-machine interface. The embedded system that we are talking about is basically a three-tier system, wherein firstly we are interacting with the hardware, and then the hardware, and actually we are not interacting with the hardware directly. We are interacting with the hardware with the help of a programming language, and that hardware is in further interacting with the sensors. And in case I want to control the temperature or the pressure, so that thing is basically the controlled object or the controlled parameter, and that basically forms a three-tier structure, wherein there is a man-machine interface and there is the instrumentation interface. That means the hardware is interacting with the instrumentation at the further level, right? And then we have the CPU utilization or the time loading factor. This basically specifies that how much of the time the CPU is idle in comparison with the amount of time that it has spent on actually doing something. For example, in case I take the case of transfer of data between any two devices, then the transfer of data has to occur at the same speed, right? So for that same speed, it is but obvious that in case the controller is running at 100 megahertz, then the device also needs to run at 100 megahertz. Otherwise, it won't be able to capture the data that the controller is sending. So in that case, suppose I have a device that is running at 10 kilohertz. Controller is very fast, so controller will have to slow down, and that slowing down of the controller basically involves the use of wait states. That first I'll send data and then wait for specific amount of time, because I know the receiver cannot receive that much quickly. So I'm sending a data for a very small interval of time, then waiting for a very large interval of time. That idle time is what basically is represented in the CPU utilization factor. Generally, it is considered that in case the CPU has around 70% utilization, then it is an optimal device. 80% of utilization basically depicts that the system is nearing its overloading range. Why it's nearing its overloading range? Because after 80% of utilization, in order to include some of the extra functionalities in a system, it becomes really difficult, because at that point the controller will be working around 90 to 95% of efficiency, and 90 to 95% of efficiency we generally do not consider should be working on, because we have just 5% of leverage, which is not sufficient in case the worst case conditions of execution of tasks are to be considered. So that's why we consider that 70% is the optimal point, whereas 30% and 10% are the underutilized conditions, wherein the controller is interacting with very slow devices or has ample amount of modifications that can be made into the program, and new features can be added to the embedded system. Now, this is basically the classification of the real-time systems, wherein we have the soft real-time system, hard real-time system, and the firm real-time system. About that, real-time systems are time-bound. Time-bound consequences have led us to the classification of these real-time systems, because all of these systems are time-bound. But what is the difference between all of these systems is
అది మందే ఇప్పుడు మందే ఆనే కొడుతుంది అది మందానే
system, but that missing of the deadline will not cause
cause
disastrous
disastrous
consequences
consequences
or
or
not
not
risk
risk
the
the
life
life
of
of
any
any
other
other
person.
person,
Right?
right?
The examples that in case we consider a soft real-time system, we can take it as an automated teller machine. So uh, I cannot say that it is a disastrous consequence. It will be a merry day for the person for whom the soft real-time system is working in that fashion. Because once you insert the ATM and in case the machine hangs up, then you are the richest person at that very point of time, right? So these are the soft real-time systems wherein disastrous consequences won't result. It won't risk the life of any person. Then we have the firm real-time embedded systems. Now, firm real-time embedded systems are the systems wherein the failing of equipment will lead to some amount of disaster, but that might not be linked with the human lives. Why over here we can see the destruction of the crops, and these destruction of the crops has been done with the help of a weed killer. The weed killer is basically a machine or a robot or autonomous device which goes through the farm fields and detects that where are the weeds with the help of image processing, right? And in case that weed killer has started to hang up and is not able to detect what the which are the weeds from the actual plants that have been planted, then in that case we have the probability that the weed killer might kill the crops also as compared with the weeds. So the entire crop might go wayward, destructed. But that is, though consequence is disastrous at that very point of time, but not linked with the human lives. The human life is not risked, though the financial losses do occur, right? So in that system wherein the missing of the deadline will cause harmful consequences but not lead to disastrous or accidental cases is referred to as a firm real-time system. And moving on to the last one, that is the hard real-time system. These are the systems wherein we have the destruction of human lives also, or involves huge financial losses in terms of hundreds and thousands of millions. So those losses wherein the system once misses its deadline will lead to a devastating effect is referred to as the hard real-time system. For example, the image shows the destruction of a spacecraft. So in case the real-time system in a spacecraft is failing, around 15 to 2000 million dollars are the financial inputs in this making of the spacecraft. So this destruction not only demoralizes the person who had invested in it, but also demoralizes the person who had developed the system for it. That it is such a big and rich clubbing together of the embedded system, it becomes really hard to find that where the problem was in the embedded system. So that devastation also includes the human life, and in case it is not an unmanned aerial vehicle or unmanned spacecraft, then the human lives are also risked. And we have the example of the Discovery spacecraft that went off while it was on its way back to the earth. We lost the lives of Kalpana Chawla also over there, right? So what are the basic requirements? Yes.
You were talking about the particular application of the formats of
Mm-hmm.
type of the real system, but if you have to, find draw a silver lining between, real time and soft at all. What
Mm-hmm.
is exact difference regarding time, criticality of time?
Regarding the criticality of time, I would say that soft real-time system is one wherein, for example, I can take that of a any of the blogs. I given a message that I need answer for this question by tomorrow, right? And because I have some sort of arrangement or any of the presentation, and that thing is though critical for me, but I might not get the response within that stipulated one day. And in case I'm not getting the response, then that thing is very much clear that I'll be shifting on to different arrangements also, right? But I cannot say that after not getting the response from that blog will lead to the destruction of my any of the physical parameters, or will lead to the ruining of my PPT, because I have different options and blog was just one of that option, right? For example, we can say the measurement of temperature. I have a device that is giving me result in every 10 seconds of temperature, but in case I am measuring the temperature after 5 seconds itself, not waiting for the 10-second time gap, so I'll be getting the temperature that was existing 10 seconds prior, not the current temperature. So that thing is not going to put in a pressure, because within 5 or 10 seconds of time gap, the temperature cannot move on from 30 degree to exactly 50 or 55 degrees. So that is a soft real-time system where you do not have very devastating effect. But firm hardware real-time system involves large financial losses. But later on, in case it comes back to its normal working operation, then the things can move on smoothly. Fine. Now, these are the functional requirements that we analyze are required for real-time operating systems, real-time systems. I'll not use the term operating system, but because that is the term that will come later on, and what basically that is we'll be discussing. And functional requirements of the real-time systems includes that it needs to be sensitive to the inputs. It needs to be sensitive towards the controlling of the outputs. And the third thing that a real-time system needs to perform is to gather the data. For example, a real-time system, if I'm considering a real-time system of measuring the temperature and the pressure and the atmospheric humidity, then that thing has to be performed at a very regular rate so that I can gather the data and analyze that what is the sequence of these variation in parameters and what is the weather going to be in the next few months, right? So that real-time system will be concerned with basically gathering at each instant of time what is the temperature, what is the pressure, and what is the humidity. So all that gathering of the data is first functional requirement. Second is, it is to be sensitive to the inputs. For example, if I press a button on it, then it should show me the present scenario, that what is the temperature, pressure, various other parameters. And third thing is, it has to be sensitive to the controlled devices also. Means in case the temperature or pressure increases beyond a certain limit, then it should be capable enough of controlling that temperature and pressure itself, or issuing an alarm. In case it is not capable, then it should issue an alarm within a specified time. That is the basic requirement of a real-time embedded system. Now, this is where the RTOS comes into play. Till now, we were discussing about the real-time embedded systems. This has to be very much clear in our mind that we were not involved in any way with the software working on the embedded system. We were actually discussing about the hardware part, that a hardware should be behaving in this manner, and the different architectures we have for the hardwares. We have the von Neumann architecture, we have the Harvard architecture, and all those architectures vary in how they execute a particular process, and those architectures are basically within the IC itself, right? There is no programming model at all over there. So those things were physical in nature. Means the real-time systems that we were discussing were physical in nature, but there is a requirement that in case the hardware is not sufficiently approaching the goals that we require, then that hardware needs to be molded in order to act in a real-time system manner, and that has to be done with the help of a software. Either that software can be the C programming that you are doing, means you design the system in such a manner, you do the programming in such a manner that every time the task that should have the highest priority is performed. Priority issuance is the biggest concern of a real-time system, because a real-time system has to gather data from multiple inputs, but which is the data it will be processing, at what point of time, and who has the most critical result needs to be performed at that specific time are the issues that are to be dealt with the programming. So in case you are capable enough, you can do it in embedded C also, or any other language. The programming can be done in that manner. In case we have seen that as the embedded system development has advanced, we have seen that the the number of applications which an embedded system is controlling has been increasing day by day exponentially. So to program for all those applications or all those control parameters, it becomes really difficult. So we have devised a method wherein we are not controlling the hardware actually directly. We are just giving the inputs, that what is the most critical parameter which we want to control, and that has been made with the help of RTOS, the real-time operating system. Now what RTOS is, that initially we had the hardware, then we did the programming on it, and we were actually linked with the controlling part of the hardware. We were actually dealing with the registers inside the controller, and inputs and outputs, we were controlling them directly. But now what we are doing is, we have the hardware, then we have the kernel layer of the RTOS, and then we are at the top end. We are giving the input to the kernel is then deciding that how should I manipulate, how should I make the hardware work in order to get the real-time function out of it. That is referred to as the real-time operating system. Otherwise, in case RTOS is basically a further classified class of the operating system itself. We have the microprocessor also, Intel microprocessor in our laptops. We have them in computers also. But that operating system is not real time. Why it is not real time? Because in case it misses a deadline of playing a specific alarm, or for example it is playing a video and misses out or hangs suddenly and closes the window, that is not real time. But embedded system is to deal with real-time objects only, critical objects only. So those critical objects need to be controlled with the help of a real-time operating system, wherein you feed in the input to the operating system that these are the parameters that I want to control, these are the parameters that are most critical to me, and those parameters are then further controlled with the help of the software or the operating system that we are loading on the hardware. That is referred to as the real-time operating system. And this is the heart of the real-time operating system. Everything is considered or viewed with the help of a task only. In the beginning of real-time systems, we had the discussion that it is a perception. What is a real-time system? It is a perspective that we are either doing the tasks procedure-oriented or object-oriented, right? Over here, the main object is task execution, and that task execution is basically we know that at one instant of time, only one task can be done. You cannot execute multiple tasks at one instant of time in case you have just one controller. We have the dual core processors also, quad core processors also. We had the single core processors, Pentium processors we had. Why we are having different cores? Those different cores are basically different processors that are executing independently and can execute multiple tasks. That means two controllers at same instant of time will be executing one task. So we have two tasks executing just at one instant. But that was at the expense of increasing the processor, right? But in case of a real-time embedded system wherein we have just one processor, we cannot execute multiple tasks, and that execution, but we want that the tasks should be multiple. So a hallucination is created wherein the time gap is divided into slices, and each task is executed for one specific slice of time only. And over a period of time, if we have three tasks executing, it'll over a period of time it'll be viewed to us as if the entire three tasks are executing simultaneously, but processor will be executing very small portion of that task at very small instant of time. That is referred to as the time division multiplexing, in case in raw sense or layman sense, if we refer to it, right? So the RTOS is basically concerned with the execution of task only, and that task is to be concerned with whom to assign the highest priority and which is the task that needs to be executed. So as to, for example, in case I have a fire alarm system, and I get a signal from one of the sensors that there is a fire system, what is the most important task? Is it to give the output to a display system, or is it to generate an alarm in order to douse off that fire? Generation of an alarm is the most priority task over there to me. So that task management related issues, how the RAM is going to be allocated to specific task, and how that task will be accessing the resources of the CPU, is referred to as the RTOS working operation, right? And herein we have a number of terms also. We have mutexes, we have semaphores also, and all those things basically deal with how a specific task will be assigned the memory to it, and how that memory can be accessed by other tasks also, right? Now I'll be showing you another video regarding the real-time embedded systems. That's how they are critical. That what the results of real-time system, hard real-time system missing its deadline can be. And in case a real-time system fails, though it might not miss its deadline, but in case it fails, then what the consequences can be. For example, they on a very general note considered, मैम चलता रहेगा. The spacecraft that was launched in the space in the video was basically that they were assuming that a 64-bit number will be reduced to 1/10, and that will be the decimal part will be all zeros, but that was not the case. So that very negligible amount of time lag basically in propelled the spacecraft to go out of order, and ultimately they had to press the panic button and destroy it in midair. That was the case over there. But what was the case in case of Scuds? The Scuds that he was talking was a modification of the Iraqis, but not a modification within the real-time embedded system. The real-time embedded system was very much on its target, but due to the wobbling effect of the Scuds itself, it could not meet its target. So the failure of a real-time system to achieve its target also leads to very harsh consequences, and that can lead to loss of life. So these were the basic introduction of what the missing of the targets can be. Then we move on to some of the misconceptions related to the real-time system, and these misconceptions are basically that real-time systems are very fast. This is a myth that has to be broken, that real-time systems need not be very fast. Real-time systems need to be time-bound, because in case of the Patriot missile that we saw in the image, the system was time-bound, and it had the amount of time from the launching till it had the struck its target. It had that amount of time in order to realign its position, and that is what including from 1 to 2 seconds of time. That is not a small amount of time at all. So in case we are considering the real-time system, then it is not the fact that they will be fast in the nature itself. Then the rate monotonic analysis has solved the real-time problem is another misconception. Rate monotonic concept is basically assigning the highest priority to a task that has the highest frequency of occurrences. Means the more number of operations that I have to perform on a specific task will be considered to be the process that has to be executed with the topmost priority. That is another perception of viewing the real-time problem and finding a solution for it, but it is not the ultimate solution. Till now, we have not been able to find a specific or a unified system of operation for a real-time system wherein we can assign priorities correspondingly to it. Then there is need to build a real-time operating system, because many commercial products exist, but these commercial products are varying in degrees. They are catering to different processes. So whatever you want to develop regarding your specific application will be considered in your time perspective for the real-time operating system. Okay, now finishing up with that real-time part, we'll be discussing about the definition of a distributed system. That till now, we have been we have reached till the state wherein we have discussed the embedded system, then we have discussed the real-time system, and now we are discussing about what are distributed systems. Distributed system is the biggest application that has been made use of by the automobile industry, because in automobile what we are facing a challenge is that day by day the number of moving mechanical parts are reducing and the number of increasing electronic parts are evolving. And why is that happening? Because sensors are occupying very less space or very compact space as compared to the larger mechanical devices. So in order to sense the temperature, just the
problem that we are facing in distributed systems is that we need to make the systems very much accurate in the transmission of the data. That means an automobile, when we are considering, will not be having just a single sensor. We have the light sensor also, we have the camera attached also, we have the temperature sensor in order to cool the entire atmosphere within the car premises. Then we have the engine control unit. Then we have the unit in order to control the transmission part. We've heard about the automatic transmission. Then who is performing the automatic transmission? That transmission is being performed with the help of electronic circuit itself, or the embedded circuit in general, in specific, I can say. So that thing is basically the distributed part, wherein you have different and small computation modules running at different parts of the vehicle, but they need to respond to a centralized unit, or a centralized unit needs to control them, needs to gather the data from them, and ultimately provide the desired output, right? That
basically a distributed system is. Means computation part is not now at a central node. It is occurring at different nodes within the specified premises, and those specified nodes are then controlled by a central main controller or a number of central main controllers. Okay, now we've discussed about the distributed systems also. Now we'll be discussing about the practical aspect, that what are the protocols that are used for the communication between those distributed real-time embedded systems. The general protocols that are used are either the USART, Universal Synchronous Asynchronous Receiver Transmitter. It is a serial mode of communication. Then we have the very basic and the most common communication protocol, that is the parallel communication, wherein we do not need any clock synchronization. We can directly send the data in parallel bits, right? In serial, what is the case is, we reduce the number of wires, we send the data on just one or two specific wires. And why it is being used is because, first of all, for short distance communication, parallel communication can be realized, and that is the scenario wherein we are talking about the internal structure of a IC. Within the IC, I will prefer parallel communication because there the distance is very much low and I need very high speed within the IC. But external to the IC, as the distance increases, the operation of the parallel communication degrades. As the frequency of transmission of data also increases, the effect of inter-symbol interference occurs in, and that thing causes the disruption of the data. That is why we prefer serial communication as compared to the parallel communication. And why is we are preferring the serial communication as compared to parallel communication, and why does the inter-symbol interference occurs is because in parallel communication we have parallel wires. All of those wires are carrying data, and in case we consider two adjacent wires, then on one, suppose I have a one signal high level, and on the very next wire I have a zero level. So what is basically this thing? I can consider two parallel wires. On one wire I am giving a 5 volt, on the other wire I am giving a 0 volt, and that basically makes a capacitor. Capacitor is nothing but voltage applied to it with a separation of dielectric. And the wires that you design on a board, the board is made of epoxy resin, and that itself is a insulator, and the capacitor includes an insulator within it. So in case the distance between those two wires is very less, and you have a high voltage and a zero voltage over there on the adjacent wires, then you are basically creating a capacitor itself, and that capacitance is within those two adjacent wires. But you have multiple wires, so all those capacitances will come into effect, and that will cause inter-symbol interference which will cause the charge to flow from one point to the other, which may cause, so that may result into the distortion of the data. You might have sent something else, received something else, so that effect is nullified wherein you are transmitting data on a single wire in serial communication. That is why serial communication is preferred. Also, it does not degrade with respect to distance as the distance increases. But the challenge is to evolve systems wherein serial communication can be made dependable, and those communications can be made cost effective also. So the uh, protocols that we are going to consider are the I2C protocol, the inter-integrated protocol, and the CAN bus protocol, which is widely used in terms of automobile industry. And the CAN bus is one of the patented protocols which has been considered to be a milestone, wherein which has been applied to the all the automobile industry, and Robert Bosch was the inventor of this protocol. Now, we'll be quickly going through what I2C is basically. I2C is basically a two-wire communication system wherein you have two lines, the SDA and the SCL, the serial data and the serial clock. The data will be transmitted on the serial data line, and the clock will be given by the master. It is basically a master and slave topology, wherein you have a transmitter that will be the master, and all the other nodes that are capable of just receiving the data will be the slaves, right? And out of those nodes, the person who will be receiving the data will be the specified slave or the active slave. So the master will be transmitting only to the particular slave, and we have been able to achieve 100 kbps and 400 kbps speed in I2C communication. And for high speed I2C bus, we have been able to achieve around about 2 to 4 mbps of speed. Now, these things we've already discussed, that it is a two-wire protocol, synchronous in nature because we have a clock line, so it will be synchronous, and we have a master-slave model because the master will be transmitter and the receiver will be the slave. Then bidirectional data transfer can take place. Means either you can write to a device or you can read from it also. So that basically nature is a bidirectional nature, right? And it is a serial interface. At the very beginning we discussed it. This is basically the model of the I2C protocol, wherein the pins used for the master and slaves are they are open drain boards. Open drain in the sense that they cannot communicate until and unless you make the adjustment of a pull-up resistor. So these pull-up resistors are required, and after attaching the pull-up resistors only the communication can take place within the two devices. Now these are the protocol signals, that what is these, how will one master device or how will any of the device indicate that I want to start communication. So that thing needs to be done with this physical parameter, that first the SDA line will be brought down, pulled down by the master or whosoever wants to gain access to the bus or the I2C bus or wants to communicate with a particular device. So first the SDA line will be brought down, then after a time gap of 15 microseconds the SCL line needs to be pulled down. This is the indication of a start condition. So once the start condition is there, then you can start the communication. We'll be discussing the entire process, how the communication takes place. But for the start condition, the first thing is you bring down the SDA, and 15 microsecond time gap you bring down the SCL. Then the stop condition, once you have completed the entire communication, then the master will first release the clock signal, and then after 15 microsecond gap it will release the data signal. That will indicate the entire bus is free. Now any of the other devices can also start communication. Until and unless there is a stop condition, no other device can give in for a start condition. This is the repeated start condition, that once you give a start, then ultimate end should be with a stop condition. But a repeated start condition is basically means first giving a start, then performing some task, then again giving a start. That is also used for reading the device. Means in order to read the device, first you need to give a start, you will perform some functions, and then again you will be giving a start condition for indicating that I want to read your data. So that thing is inculcated in it, and we'll be further discussing the repeated start condition. Then this is the acknowledgement condition, that after you have transmitted the 8 bits of data, those 8 bits need to be acknowledged whether you have received it or whether you have transmitted the 8 bits properly or not. So that acknowledgement is done by the receiver always. In case I am transmitting 8-bit data, I'll get a acknowledge signal on the 9th bit, on the very next bit, that I have received it by the slave device pulling down the SDA line. In case it is not pulling down the SDA line, that means there is a error in transmission. It has not properly received the data. Then we have the write process, wherein this is basically the entire process. In case I have a transmitter, I have a master device and I have a slave device, and the master device wants to write some data to the slave device. In that case, what will the process be followed? First, the start condition will be initialized. After the start condition is initialized, the master has indicated that I am communicating and nobody else will ask for the control of the bus, right? After the start condition, we'll be giving the address of the device with which we want to communicate. Each slave has a specific address, so that address will be sent. Then after that, we'll be specifying that what specific location within that device I want to communicate with, and after giving that address, we'll be writing the data to the device. After giving the 8 bits, a stop condition will be issued, and ultimately the bus will be free for communication again. Then we have the read process, wherein we'll be using the repeated start condition. First we'll be giving the start condition, then we'll be giving the address of the slave device, then we'll be giving the location of the memory which we want to read, and then again issuing a start condition, and again giving the address of the slave device plus 1. This is the difference between the repeated start condition, that initially you gave the address of the exact address of the device, but now after the repeated start condition, you will be giving the address of the device plus 1, which will indicate to it that the user wants to read the data from my particular memory. Then you can read the data from the device, 8 bits of data, and ultimately you can issue a stop signal once you are finished with the reading of the 8 bits. Now we'll be quickly going through this CAN bus. CAN bus is basically was developed by Robert Bosch, and it is also a serial communication method, but it is very much noise tolerant as compared to the I2C bus. And how is that possible? Because it utilizes the transmission of differential signals. And what do I mean by differential signals? A high is 5 volts, a low is minus 5 volts. So in case you have noise incorporating in your signals, right? For example, I have a signal that is being affected by noise. So that noise will be in one direction for the positive signal, the other direction for the negative signal. So overall, in case we analyze the differential voltage between those signals, where the noise will cancel itself. So once the noise cancels itself, the overall differential voltage will remain the same, and ultimately the noise distortion that can incorporate within the signal transmission from one point to the other gets nullified, right? So that is where the CAN bus goes over the I2C bus, and has been doing the rounds in the industry, that almost the standard formula used for implementation of the automobile distributed embedded systems in automobiles. Invented by Robert Bosch in 1980s, and basically used to control the ECU and communicate the ECU with the other parts of the automobile electronics. Okay, fine, we are done with the presentation, and I'll just be, in case you have any queries you can ask, and in case you don't have, I'll just go on to show you the actual implementation on with the help of a simulation that how the real-time embedded system can be implemented, though we'll be implementing it with the help of AVR microcontroller. uh, I wanted to implement it with the help of ARM processor, but that thing would have been very much complex because each of the ARM processor registers varies from around about 32-bit to 64-bit. So handling those things and masking all the bits becomes very difficult and would have been impossible to uh, teach you within this specified amount of time. So I have incorporated in the AVR program, wherein I'll be showing you that what basically the real-time implementation involves. I'll first show you the okay. The image that you are seeing basically involves an LCD connected to a microcontroller, and on the other side of the microcontroller we have a device named the memory device as the EEPROM device. Its number is 240C, right? And basically it is a permanent memory device wherein we can store data, access the data from it later on once the power is switched off, and then further display it on the LCD screen, basically used for saving of the passwords or changing of the new passwords. So all those things are performed with the help of EEPROM, and this EEPROM is basically an I2C based device, means it will work on the I2C principle. And the I2C principle states that in order to read the device, or you want to first, in case we want to write this device, we'll have to start the location which we want to read, then we'll read the location and then stop condition, right? So the then writing and then the stop condition. Now what is actually happening in this program is, this is the entire program. First we'll be concentrating on this part itself. I'll zoom a bit so that all of you can view it easily. This is the important core of the entire program, wherein first we have the main program. After the main program, we have the character initialization, or means I want to write some data to the inter-integrated device. So I have made this custom function myself. We'll be seeing what this function is doing internally, and I have said that write 59 on the first location, memory location of the EEPROM device, right? So this is 59 is the value that will be showing that what is the value to be written or stored within the memory of EEPROM, and this is the location where I want to store 1. Then I have a for loop, infinite for loop, and that infinite for loop is doing that it is continuously reading this first location. Whatever data is available on the first location will be sent to the Z variable, and that Z variable will ultimately be displayed on the LCD. And now coming on to what the write and read functions are doing. This is the write function that we discussed. First I'll start the I2C signal, I'll send a start condition, then I will send the address of the device that I want to communicate with. So A0 is the address of I2C based EEPROM. Then I am sending L as the location which I want to write of the EEPROM, and L is this variable that will be 1. Right, I gave the parameter 1 to that particular function, and that one variable will be written to the device. So now the I2C bus is basically pointing to the first EEPROM location within the device, and then I'll write the data, that one, and that one was basically containing the value 59. After writing that value, I issue the stop condition. In case I want to read the device, then I have this function. First, I'll be issuing the start command. Press +1, and then we'll be we'll be reading the device, and then we'll be issuing the stop command. And what are these start conditions and stop conditions? I already told you that these are nothing but the gap variables of 15 microsecond. This is the start and the stop condition. Means initially we have the SCL and SDA as 1. Both the lines are 1. Initially they are high, and the start condition said that you need to first bring down the SDA line, and 15 microseconds you will bring down the SCL line. So what we have done over here is SDA line we have made it 0. Delay of 5 milliseconds we have given. We could have given just 15 microseconds. We have increased the time delay. That does not indicate that it will not respond. The overall response time will increase. That's the only reason, right? So we can give delay microsecond 15, and then we'll in condition first the SCL line needs to be made released, and then we'll be releasing the SDL 15 microsecond time gap. This is the basic program, and this is how the it's working in the previous, so that it is reading the memory EEPROM and ultimately displaying the result on the LCD. Another implementation which is quite complex, but we'll not be discussing, but we'll be showing you that again we have the RTC over here, that is DS1307. This is again an I2C based device. These two registers are the pull-up registers that we have used, that we discussed about in the I2C. And finally, we are displaying the time in real aspects on the LCD. After every second, we have been able to get the input from the RTC real-time clock, and we are updating that time on the LCD in real aspects. That is referred to as real-time embedded system. And once we consider the case of a number of modules working independently and ultimately giving the feedback to the main central unit, that is referred to as the real-time distributed embedded system. Okay, thank you very much. I'll wind up with this.
Now it's time for queries. So participants at nodal centers, do you have any query? Yes, JECRC, Jaipur. Participants from Alwar. From Northern India Engineering College, do you have any query, sir? Any query regarding this? Yes. Hello?
ఆల్రెడీ వేరే సెంటర్ వాళ్ళు అడుగుతాను.
Hanji, do you have any query?
టైప్ చేయమంటారు.
PVP Siddhartha, participants who are sitting at PVP Siddhartha,
Good morning, ma'am.
good morning.
Madam, while we are using the real-time system, what is meant by rate monitoring system?
Okay, ma'am, rate monotonic system is basically the process of assigning priority to a specific task. Basically, this was the concept that was included in the introduced in around about 1980s, and it was basically regarding the assignment of the priority to a specific task. For example, let us consider that I have an embedded system wherein I am getting the input from specific two of the sensors, and one of the sensor is giving me input at the rate of 10 kilohertz, and the other one is giving me input at the rate of 20 kilohertz, right? From the frequency of operation, I can judge that 20 kilohertz is the signal that is again and again interrupting the microcontroller or the real-time embedded system. So in case I have both these tasks interrupting the microcontroller and giving the data at the same time, then the task having the higher priority frequency of operation, that is the 20 kilohertz task, will be given the first preference for the execution, for the assessing of the resources of the microcontroller. That is referred to as the rate monotonic system.
Sir, one more doubt, sir.
Yes, ma'am.
While reading the address, why you have chosen slave address plus one, sir, instead of using writing program only slave address?
Ma'am, this is the protocol. The protocol specifies that in case you want to write to a specific device, then only you will be issuing the address at which you want to write the specific data. But for the read process, the protocol specifies that first the address of the device, then the address of the location that you want to read. After that, you again need to reissue a start command and then give an address plus one. That is the protocol. It's predefined. We have to follow it.
Okay, sir. Thank you, sir.
Okay, welcome, ma'am.
Yes, queries from other participants at nodal centers. Any query? So with these words, yes, yes, please go ahead.
Good morning, ma'am.
Good morning.
Ma'am, I just want to confirm the software and the version which sir used to demonstrate the previous example.
That is a protest.
Ma'am, I used Proteus, and it is basically Proteus 7.3 version. And the program editor that I was using for the coding part is basically Keel Microvision.
Okay, thank you, sir.
Okay, thank you. So with these words, I would like to thank Mr. Simranjeet. So I hope all the participants have enriched their knowledge with this vast experience. Now our next speaker, Mr. Deepak Sharma. He has already reached in our studio. So we will take a break of just 5 to 10 minutes, and we will join here again at say 11:30. So thank you, thank you.
Quite easy.
ठीक है मोनिका कनेक्टेड इन सेंटर्स ओके सो मैं इंट्रोड्यूस कर देती हूँ
ठीक है बटन लेता हूँ फिर
हाँ हाँ श्योर So very good morning to all of you. Now our next session, that is the role of embedded systems by Dr. Deepak Sharma, he has already reached in our studio. Mr. Deepak Sharma, working as senior scientist in CSIO Chandigarh. He is currently associated with MIS division and involved in the area of software engineering, wireless sensor network algorithms, and ICT management. He is recognized as an assistant professor of Academy of Scientific and Innovative Research, that is ACSIR, in the Faculty of Engineering Sciences. He has also worked on design and development of various base stations, mobile stations, simulators for multiple radio assist technologies, and he has also worked on various satellite constellation simulators. So today he will let us know about what is the role of embedded systems in wireless sensor network at the physical layer only. So as we can say that nodes are available at the physical layer, so how these embedded systems are useful in the scenario of wireless sensor network. So I welcome you, sir, in this studio, and I request you to kindly proceed with the session.
Thank you, Dr. Kanika. Systems in wireless sensor network. So, first we will be discussing what is wireless sensor network, then what are the application areas, what are the design challenges, then we will be discussing what is the protocol stack of wireless sensor network, then what are industry standards, then we will be discussing about some hardwares, about some algorithms, and then what is the future of this technology. So what is wireless sensor network? Wireless sensor network is basically a collection of large number of sensors which can interact with each other to sense some physical phenomena and send the results to our sync node where we can process the data and get the relevant output. So as you can see, there are various nodes and those nodes are communicating with each other and sending the data to the sync node, and sync node is connected to internet so that you can fetch the data from anywhere. This is a typical WSN system scenario. So why this particular technology is very important? It's due to its having a very large number of application areas, be it military related applications, be it environment related applications, health related applications, for example, precision agriculture, as well as this technology is a building block of much talked about technology, Internet of Things. So we will start with WSN node. As I just told you that wireless sensor networks are basically collection of wireless sensor network nodes. So what is WSN node? WSN node consists of four major blocks: a sensing unit, a processing unit, a transceiver, and a power unit. So sensing unit consists of your sensors. That again depends on your application. For example, if you are looking for sensing humidity, then you will be going for a humidity sensor or maybe for the temperature sensor. As the sensors are generally analog in nature, so you require an analog to digital converter. So that is basically our sensing unit. Then we are having a processing unit, so which will process the data, and having a storage unit to temporarily store the results as well as to store the algorithms. Then we are having a transceiver block, which is basically a RF block in our particular case for communication purpose, wireless communication purpose. And we are having a power unit which is going to feed all these different components. What we can see, they are having some dotted line blocks. These are basically subsystems which may or may not be required depending on our application. For example, location finding system. Okay, sorry. For example, location finding system. So location finding system is maybe a GPS chip. So that may be required. You may require that your sensor node's location must be known along with the sensor data. So you can have a location finding system, a GPS chip, or you can develop your own location finding algorithms. Similarly, there is a mobilizer. Mobilizer is required if you want to mobilize your node depending on your application. And another block is power generator, which is basically an energy harvesting system, for example, solar panels. So three main components: node design, system design, and protocol related aspects we will be covering in this lecture. So what are the influencing factor when we are designing a sensor node? So very first thing is wireless sensor networks are application specific. So whenever we are designing a WSN, we are supposed to consider for what particular application we are going to develop it. For example, what kind of environment we are going to deploy our wireless sensor networks. It may be a home automation, industry automation, it may be underwater or mobility scenarios. Another important factor is whether we will be able to place our sensor node deterministically or we have to deploy them randomly. Other requirement may be bandwidth and error rate. Similarly, hardware of wireless sensor node are constrained in battery power, storage, and computational power. Cost of overall device as well as the system is very critical factor because we are supposed to deploy very large number of nodes. So overall cost must be minimized by minimizing the cost of each and every node. Then the transmission media. For wireless application, we can go for RF, optical, or infrared. We generally go for RF, and these are limited to our ISM band. Then power consumption. So communication part of particular node is going to take most of the power. Then sensing unit is going to take more power than processing power. So whenever we are designing our system, we try to reduce communication power. So what we can do, we can put some sleep cycles whenever we don't want data from a particular sensor node so that we can minimize our communication overheads. Network scalability is related to how many number of node network can support. Similar way, self-healing and self-organizing network capability means if a node is getting failed, then network should be able to heal itself. Or if you want to add some new nodes, then network should be able to self-organize itself. So multi-hop capabilities are required for these two particular applications. So these are some well-known topologies. For example, pair is your point-to-point. Star where your end node are directly communicating to coordinator. Cluster tree-based approach where end nodes are sending the data to cluster head. and cluster head are further sending it to coordinator. And the mesh network are the most important in our particular case, because as you can see, all the router nodes are connected to each other. So this is required for self-healing and self-organizing capabilities of wireless sensor network. So this is a typical example of mesh networking. For example, I want to send some data across this network. So these routers or these nodes are connected to each other, and I have defined, okay, that I will be sending the data from this red path. But what happens if two nodes dies during this particular operation? Then our network should be able to self-organize itself. So that is how the mesh networking works, and it's a very important aspect of wireless sensor networking. So now we will be going towards WSN protocol stack. So you must have seen OSI protocol stack, which is having 7 layers. So functionality of any protocol stack is more or less same. But what you can see here is it's a 3-dimensional protocol stack rather than 2-dimension. You can see 3 planes here: a power management plane, a mobility management plane, and a task management plane. So what does it mean? It means that whether you are working on physical layer, whether you are working on network layer, or you are working on application layer, you are supposed to consider these 3 aspects. So what is a physical layer? Physical layer is where you are going to consider what kind of modulations you are going to use, what will be your transceiver design, what kind of data encryption you are going to use, and your propagation effects. For example, if you are considering a direct line of sight communication for RF, then you are supposed to consider a d² loss. But if you are going for a multipass scenario, then you are supposed to consider n to the power d to the power 4 loss. So depending on what kind of environment you are going to deploy a node, you are supposed to consider a corresponding propagation model. Then data link layer is concerned with how you are going to access your medium. For example, carrier sense multiple access collision avoidance. This is a pretty old technique, but is still being used in WSN, particularly 802.15.4 standards. Then what are the power saving modes, as well as what are the error control measures you can take? For example, you can take forward error correction codes, or you can go for automatic repeat request. The network layer is related to your routing and data aggregation. And as we discussed earlier, that whether it's network layer, you are going to consider your power, task, management aspects in this particular layer as well. Your transport layer is related to how you are going to integrate your network with other networks. And application layer is where you actually going to say what kind of application you are going to develop and what kind of functionality will be there in your application. For example, sensor management protocol is one such protocol. There are other protocols like MQTT is another such protocol which is used in telemetry and transportation. So now we will be moving towards what are the well-known standards in WSN. So IEEE 802.15.4, Zigbee, 6LoWPAN, wireless HART, and there are a lot of proprietary solutions from a lot of vendors. So what is 802.15.4? These are the standard from IEEE, and they basically define physical and MAC layer of our protocol stack. And the upper layers are maybe different depending on our different scenarios. For example, the upper layer may be Zigbee, 6LoWPAN, wireless HART, ISA 100.11a, etc. So 802.15.4 basically works in ISM band. In India, it's 2.4 gigahertz. It supports up to 16 channels. At media access level, it uses CSMA CA. and it uses quadrature phase shift key for modulation. And but the point to be noted here is not supporting the mesh. It's basically supporting the star or peer-to-peer network. Lot many vendors are already there which have developed kit based on 802.15.4. So two kind of chips are there, either radio only or system on chip which is having radio and transceiver as well. So another protocol is Zigbee. So Zigbee is based on 802.15.4 standards. So PHY and MAC layer will be from 802.15.4 and upper layer will be developed by, actually they have been developed by Zigbee Alliance. Zigbee Alliance is supported by large number of industries. Some are well-known name are there like Philips, Siemens, Samsung, and this is our Zigbee stack. So PHY layer and MAC layer are same as 802.15.4, and network layer is basically considering the routing part. Normally it uses AODV in their network layer. Then application subsystem layer, which is a bridge between the network layer and Zigbee device object layer. And Zigbee device object layer is basically Zigbee device object layer basically defines whether the node is going to work as a coordinator, whether it's going to work as a router, or it's going to work as an AND node. And then we are having application layer, which is as specific to what kind of application we are going to develop on Zigbee platforms. They are having different application profile depending on different kind of requirements. So this is again the application support layer, and this is the DO. So this is a Zigbee network architecture. So in Zigbee network architecture, we are having a Zigbee coordinator, we are having some Zigbee routers, and we are having some Zigbee end devices. So Zigbee end devices are basically reduced functional devices which do not have routing capabilities. So whenever we are supposed to send the data from an end device to our gateway, for example, a coordinator node, we are supposed to send the data either to the router or directly to the coordinator. So router nodes are having the routing capability, and coordinator nodes can work as a gateway as well, where it can be connected to the internet. So these are some properties, like they are reliable, they are scalable, they are low cost, they are secure, they are using AES 128 encryption, and as you can see, they are supporting the mesh topology, which is very, very critical in our particular case. So Zigbee has already proved that it can be deployed in large scale wireless sensor network scenarios. For example, you can see like over 1000 node has been deployed in a particular hotel. So depending on different applications, they have developed different application scenarios or application profiles. So they are having home automation profile, smart energies, healthcare, R4C is radio frequency for consumer electronics. So it's related to, for example, you are having a one remote which will be working on RF and will be controlling all the devices of your home. So in this image, you can see the very first image where few bulbs are there and one coordinator is there, which is this is example of basically Philips. This is a Philips Hue, which is an example of smart lighting. So smart lighting, it's supporting Zigbee smart lighting protocol standards. It's having a router. Okay, it's basically there is a box which is working as a coordinator, and all the bulbs are communicating with this particular coordinator. So, and it can be plugged in to your Wi-Fi router, or your it's having RJ45 jack, so you can connect it to the network and you can control these devices through your mobile phone. So such kind of functionality is there in Philips Hue. This is a comparison of Zigbee with other technologies. As you can see that ZigBee is having low data rate, medium range. It can support mesh protocols, mesh topologies, working in ISM band. Device complexity is low and power consumption is very low. So there are a lot of commercial available chips available for ZigBee. But if you want to develop some applications yourself, then you can go for this XB modules. So these XB modules, there are two series, series 1 and series 2. Series 2 is basically ZigBee supported, and they are having some digital as well as analog input output pins. So you can directly connect your sensors to these chips, and you can configure these chips in a WSN network. Another interesting application of these chips are you can integrate these modules with your Arduino or Raspberry Pi, and depending on your imaginations, you can use them in variety of applications. Another standard in WSN is 6LoWPAN. 6LoWPAN stands for IPv6 over low power wireless personal area networks. So what does it mean? It means that we are going to assign IPv6 addresses to our sensors. So as you can see in the network diagram, what we have done, like we have addressed our nodes with IPv6 addresses, and there is a edge router which will be converting our v6 address to v4 address for routing purpose, because our existing networks are still on IPv4. So lower layer of 6LoWPAN are still 802.15.4 standard, and the upper layer, like 6LoWPAN layer, the standard has been given by IETF. So IETF is a body which has earlier developed various well-known standards like TCP, UDP, and HTTP. So they are having a small packet size of 127 bits, and the addressing is 16-bit short or IEEE 64-bit extended media access control address, and they support up to 250 kbps of bandwidth. So these are some hardwares available for 6LoWPAN, and as you can see, there are some operating system has been mentioned like TinyOS and Contiki, which are used by wireless sensor networks nodes. So this is one example of 6LoWPAN based network. So Vastmode is one such chip available in the market. So it's having two devices. The one, this is the end device, and the second one is gateway. This is a schematic of their chip basically. So as you can see, your end device will be communicating with each other, and they will be connected to your gateway. Your gateway will be doing a IPv4 v6 tunneling, and then you can, if you are having a IPv6 network, then you can go for a v6 network as well. So this is an example of existing WSN hardware. So this is a case of ZigBee based chip. It's by Zenic. So this is our coordinator. These two with antenna are a router, and these two without whip antenna are our end nodes. So this particular kit has been already assigned some addresses and some names. For example, it has been configured in home automation mode. So our coordinator is showing the temperature 21 degrees Celsius. So all these particular modules are having built-in temperature, light sensors. So as you can see that, like when I switched on this particular coordinator, I am able to see that okay, the temperature at this particular location is 21 degrees Celsius. Then when I switch on to coordinators, then there are three temperature has been shown. So it shows that what is the temperature at each and every node. Similar way, we can add, we have added here the add node as well, and we can see that we are able to see the temperature from different locations. This is just to show like if we are covering the photo detector, then how is it going to affect? So till now we have discussed what are the issues related to wireless sensor node design and wireless sensor network design. So now we are moving towards WSN algorithms. So WSN algorithms are required, are need to be first simulated in simulator environment, and then once it's clear that they are having some advantages, then we can test them on test beds. So NS2 NetSim are well-known network simulator for WSN, and we can also do the simulation in MATLAB. So these are some WSN algorithms. For example, what is node positioning? So node positioning is how we are going to position the node. For example, if we are putting the node deterministically, then at what particular locations we should put them to increase our overall energy efficiency. Similar way, node localization is related to finding the location of the node. For example, we discussed earlier, GPS module can be used, but we can develop our own localization algorithm based on, for example, multilateration or triangularization techniques. Then another very important aspect is energy efficient routing. So routing is related to how the message packet will be going from one node to another, like what particular path will be assigned to our message packet when it's traversing our network. Then data aggregation is related to, for example, if the nodes are nearby, they will be sensing the same phenomena and there will not be much difference in their reading. So what we can do the aggregation, and we will be sending the final results rather than sending the data of each and every node. So this will reduce overall number of bits sent over the networks. So the communication overheads, or we should say the energy, will be decreased in this particular by using the data aggregation techniques. Cross layer optimization is related to you are considering multiple layers for our for developing the energy efficient wireless sensor networks. Heterogeneity considerations are, for example, your nodes. Generally, it's considered that all the nodes are having same capabilities, like they are having same battery power, they are having same antenna. Heterogeneity is related to what happens if some nodes are having more energy, some nodes are having more capable antenna. So such kind of considerations are part of your heterogeneity considerations. Similar way, what is the network security? So what kind network security is related to what, for example, message encryption may be a part of network security. However, network security may be implemented on each and every layer of a wireless sensor network. Quality of service is to decrease the error rate, and multi-parameters optimizations mean that you are trying to optimize various parameters in a single go. Then there is network dynamics, means you are considering the node mobility if you are going for a mobile node environment, and then integration of sensor networks with wired network. So that is basically connecting your network with internet. That is a basic building block of Internet of Things. So as a case study, we are considering some routing algorithms here. So very first algorithm, if you see, like this is a direct transmission. So there will be a r to the power n loss depending on what kind of model you have considered. Then there is a minimum transmission energy routing. So in this particular algorithm, what we are trying to do, we are trying to minimize the d square loss. For example, if I have to send a message from A to C and my loss is d square, then if I will be sending the message from A to B and B to C will be energy efficient rather than sending the message from directly from A to C. The another technique is clustering. In clustering, what we do a grouping of nodes which are physically nearby, and then we assign one node as a cluster head. So whenever we are having some data to send to our base stations, the node will first send their data to their corresponding cluster head, and the cluster head will then send the data to the base station. This is to show that how the nodes will die when you are using different techniques. For example, if we are going for a direct routing, so the node which are farther will die first. And when we are going for minimum transmission routing, energy routing, then the node which are nearer will die first because they will be participating in each and every message communication. And if we are going for the static clustering, then our cluster heads will die first because every time they will be sending the data to the base station. So we are considering here one such protocol which is known as leech. This is the most cited work in WSN, and this is based on clustering based routing algorithms. So as you can see that nodes are divided into the clusters. They will send the data to the cluster head, and cluster head will further send the data to the base station. So this is a similar to the static clustering, but what we are actually doing is we are changing the role of cluster head during of course of the time. Means we will be changing cluster head will be rotated among the nodes. So this is how the leech protocol was developed initially. Like they simulated this particular algorithm. They designed environment, not an environment. They simulated the environment. Like they have taken 100-meter by 100-meter area, and they deployed the road nodes randomly. They have taken the base station at a particular location, and they have taken a first order radio model, and then they have taken the various parameters of nodes, what will be the energy loss in different components. Then this is the protocol. The protocol is having two steps. One is the setup step, and second one is the steady state step. So in the setup step, we are forming the clusters. Forming the cluster means we are choosing the cluster head nodes. And then once we have chosen the cluster heads, then we will be sending the data in steady state phase. This is a mechanism by which cluster heads are selected. And once the cluster heads are selected, we will be sending the data in a steady state phase. So this is how it works. Then blue circle is our sync node. So first we decide our cluster heads. Then once we have decided the cluster head, then cluster head will send a broadcast advertisement. It says that, okay, we have been chosen as the cluster head in this particular round. So all the nodes will be receiving these messages, and they will measure the radio signal strength of these messages. And depending on their radio signal strength, they will choose, okay, we want to join you, and they will send a node transmit membership signal. So this will decide that how will clusters will be formed. So once the cluster has been formed, head will broadcast the schedule. This is a TDMA schedule, and each node will be assigned a time slot for sending their data. So now each node will be sending their data in their assigned time slot. So once cluster head is having the data from each and every node in his area, then it will send the message to the base station. And after a number of rounds, this process will repeat itself and new cluster head will be selected. So as we have randomized the cluster heads, there will be no burden on a particular node as it has been selected, a cluster head in case of static clustering. So these are the results. So it was shown that it was very advantageous over existing protocol like MT and static clustering. So this is a quick recap like what we have just discussed and what is the future of this technology. So WSN work was started in late 90s or early 20s. So Smart Dust was one such project, which was where it was considered that we will be developing such kind of sensors which will be very smallest size and which will be able to form a self-healing network. And if you are throwing these sensor node like a dust, and you will be able to sense the physical phenomena. Something like that was considered when they conceptualized smart dust proposal. Then in 2000, Berkeley mode came into the market. Then various protocol standards was developed like 802.15, 15.4, Zigbee, etc. So what is the future of wireless sensor networks? So this is the latest Gartner's hype cycle of emerging technologies. So what does it shows? What does it show that what all technologies which are going to play a major role in coming time? So for example, Internet of Things, which is right now on top of inflated expectations, and it's going to take 5 to 10 years to mature. And there are some other technologies as well. For example, connected homes, IoT platforms, and if you see there is a smart dust as well, which shows that it's still going to take more than 10 years. So wireless sensor network is still going to stay. And if we look at IoT framework, then wireless sensor network is the building block of our IoT systems. So basically you are fetching various physical uh, phenomena through sensors and sending these information to clouds. The information will be stored in the cloud and your applications will be able to fetch the information from the cloud. That is basically the a basic IoT framework, and WSN is there in the lowest layer. And this is the technological roadmap, which has also shows that wireless sensor network will be there in coming future as well as uh, say 10 plus years and beyond. So there are large scale wireless sensor networks, there are smart traffic, intelligent transportation systems and logistics. So WSN systems are going to stay for a long time. So with that, I would like to say thank you, and if you have any queries, then please let me know.
ఇక్కడ ఇక్కడ క్లిక్ చేయండి. ఇదైతే దీన్ని క్లిక్ చేయండి. కనబడుతున్నారు అందరు, మీరు కనబడాలి కదా. హలో సార్, అన్నది ఒకసారి.
Hello.
వచ్చేసి
Sir, very good afternoon.
Good afternoon.
Sir, actually, I'm from PVP Siddhartha.
Okay.
My name is Habib.
Okay.
While discussing about the leech protocol, you have said that uh, there will be a cluster head and slaves. A cluster members will be forming clusters, right? So my question is, cluster head will release advertisement towards the cluster members. So, for example, I have 50 sensors in a network. In that,
Okay.
5 sensors has been nominated as a cluster head.
Okay.
So these cluster heads will send the advertisement mode to the remaining 45 sensors to frame a cluster.
Okay.
So on what basis the sensors, the remaining 45 sensors will select the cluster head? On what parameters?
Actually, they will be sensing the radio signal strength of these. For example, if you are a sensor node and you are receiving this advertisement message from two different cluster heads, so you will check what is the radio signal strength of both the signals, and whatever wherever there is a higher signal strength, you will be selecting that node as a cluster node.
Okay. Sir, one more doubt.
Yeah.
You have told wireless sensor network simulators like NS2, NetSim, ComNet Plus, or MATLAB, etc. Now, nowadays, people are working with NS3. So, can you tell me the difference between NS2 and NS3 network simulator 2 version and 3 version?
Actually, NS3 and NS2 version are like NS3 is the next version of NS2, but that depends. Like NS3 may or may not be supporting all the protocol. For example, if you want to going for a leech, so leech was developed in NS2. So first they developed the leech in MATLAB environment. If you will see the first paper by the author, they developed the algorithm in MATLAB environment and they re-verified their result in NS2. So whenever you are going for any simulator, you are supposed to check what is your requirement. So whether these particular protocols, for example, want to go for NetSim. So NetSim, you are supposed to check if you want to implement Leech. So Leech is already there or not. Otherwise, you can develop your required algorithm as well. So that's how it works.
Hello, sir. Sir, we
Yes,
are
ma'am.
sir, we are from IGDTUW Kashmiri Gate.
Yes, ma'am.
Sorry, Kashmiri Gate, Delhi. And our Vice Chancellor is here presently, and we were going through this lecture. She needs to ask a query here.
Yes.
Dr. Deepak,
Hello.
your solutions are mostly around Zigbee, which is a very expensive network, and I thought that can you suggest a cheaper solution using Bluetooth? Because Bluetooth is easily available in every smartphone, and a smartphone also has a number of sensors. So,
Ma'am,
what is
number of nodes which are supported by Bluetooth is comparatively less. Number one, Bluetooth is having a comparatively low range, and uh, okay, I would like to go on a particular slide where I have
compared?
discussed about what is the difference between these two.
I think the range of Bluetooth is around 10 meters, 10 to 15 meters. And Zigbee, do you think Zigbee has a longer
Yeah,
range?
ma'am, could you please show this slide? So, ma'am, as you can see, like range of Zigbee is 10 to 100 meter, and while in case of Bluetooth is it's even less than 10 meter.
Oh, I
The
see.
second thing is supporting mesh technology.
Okay.
Okay,
And
and
Bluetooth is
when we are going for Zigbee, the another reason is it's these devices are meant for very low power consumption because their algorithms has been developed in such a manner. So, for example, if you are putting a Zigbee node, it's supposed to work for a year or two or maybe for the 3 years. But when you are going for a Bluetooth based devices, you are recharging those devices where you are having Bluetooth chips.
okay.
So Zigbee are meant for long-term physical phenomena uh, captures kind of applications.
Thank you so
Have
much.
I made it clear, ma'am?
Yes, absolutely.
Yeah.
And
Thank you.
in fact, for long distance, I think applications and for smartphones, I believe Zigbee is a better option.
Actually, for example, what we can do, you can deploy a network based on Zigbee, then you can add a gateway, and that gateway can further communicate to internet, or maybe it can communicate to your mobile as well. So such kind of scenarios are already being developed, have already been developed. So this is already there.
Okay. So this is a combination of both Bluetooth and Zigbee. If we have it at last mile connectivity to Bluetooth and then remaining at with
Bluetooth may
Zigbee
be good for
at the gateway level. That's what you're
no,
suggesting?
no, no. Bluetooth will not work as a gateway label. Zigbee gateway can be connected to internet, and you can fetch the data on your mobile. You need not to go for Bluetooth in that particular scenario.
I see. Thank you, Dr. Deepak. Thank you so much.
Thank you, ma'am.
Please come forward. Get your questions.
Sir, if I want to check the characteristics of a leech protocol in a real-time scenario and that too with simulation, what approximation we will be getting in terms of output characteristics?
When you are asking about in real life scenario you are talking about, so then
Right.
you are supposed to deploy the algorithm on test bed. Okay. And on test bed simulations, you are supposed to check what are the results. So there is a the paper by the author is the second paper of this particular author. If you can see, it's in 2002 that paper has came. So they have checked, they have compared both the results. So they first simulated the algorithm in NS2, and then they what they say is that we have compared the result with the testbed simulation as well, because that project was funded by the DARPA itself. So, so you can see that paper and the comparison of both the things are there, because in one particular scenario, what they have compared, what will be the minimum number of cluster head required. So first they have done it analytically, and then they checked it on testbed. So both the things are there.
Thank you, sir.
Yeah. Okay. Thank you.
So thank you, sir. Now we will again rejoin at 2 p.m. for our next session. Thank you.
సార్ ఉంటారా వెళ్తున్నా మిడ్ డ్యూటీ ఉంది. మరి అబ్బాయి ఫోన్ చేశాను 505 పవర్కి పవర్ బాక్స్ రెడీ అవుతుందా అంటే అది 16 యాప్ కదా సార్, మన దగ్గర మెటీరియల్స్ వేయలేవు, చెక్ బోర్డు తెప్పించుకుని చెక్ బోర్డు కోసం సెట్ చేసుకోవడమే అది అంటున్నాడు. మరి ఎన్ని ఎవరు చేస్తారో
A very good afternoon to all. It's my pleasure to introduce Dr. Sandeep Singhei. He is working as a senior scientist in CSIU Chandigarh and is actively involved in R&D in optical devices systems focused towards strategic and defense instrumentation. He has expertise in the embedded system design and development for strategic applications. He has developed embedded applications for indigenous head-up displays also. He is also the convener of Intellectual Property Rights Cell at CSIO and is responsible for IPR management of the institute. He has several classified reports to his credit in addition to research publications, book chapters and popular science articles. His team has designed and developed the only indigenous head-up displays for Tejas and Sitara. So I welcome you, sir, in the studio. So now I request you, sir, to come forward and please proceed for the session.
So, good afternoon, all. I usually repeat this thing. Today, again, I am going to repeat that it is usually hard to have a lecture after lunch. So, I think all of you would have a sumptuous lunch and are available for this lecture, which I will try to make interesting and hope that it will be an interactive session which we are going to discuss on about Internet of Things basically. So can I have the feel of who all are there to? Yes, they are connected and people are available there. Okay, so good afternoon to you all. Today I am going to talk about okay, nobody is there, they are preparing. They are all sitting just camera. Okay, camera in there is issue. No issue. So today I am going to talk about embedded systems for Internet of Things. So basically I will try to cover the topic both from the research perspective as well as from the perspective of students who want to have some knowledge about the tools which are required for practicing IoT. The outline of my talk would be introduction, in which we will try to define the Internet of Things perspective, followed by various visions of the IoT paradigm which are available in the literature and on the basis of which it has been proposed in the literature a particular IoT paradigm, followed by the various enabling technologies which are required for materializing the actual vision of IoT. IoT is there today. In fact, all these technologies are also there today. But overall makes and with the projections of 50 billion devices by some 2020 or 30, in those contexts, how people will be able to manage the data volumes and all those things. Because you know internet is not a very old paradigm. Internet itself came in 1990s to the general world. In fact, I remember in 2000 around also internet was a very valuable or very rare thing. Today it seems to be omnipresent. It seems that it is present everywhere. So the various enabling technologies plus the application areas of IoT. There are vast areas, vast domains in which IoT technology can be enabled, followed by the various architectural approaches which have been proposed for IoT. Rather, these approaches are under research. They are not complete in a way to cater to the projected requirements. Then I will also discuss the various open research challenges, which are a good opportunity for any MTech or PhD student to diverge into, and followed by conclusions. Something which I might have missed in this outline is that I have also tried to name certain hardware packages which are readily available these days from the perspective of students. As far as embedded systems are concerned, we will go into detail of ZigBee. It's a IEEE 802.15.4 based open architecture or open standard for wireless sensor networks, which is a key enabler for IoT. Thereafter, if the time permits, we will discuss something about my domain, that is strategic applications, and I will share with you some interesting information about the developments for head-up display, which you might be aware or might not be aware. So, what is basically IoT? IoT, or the Internet of Things, the term was first coined by Kevin Aston in 1999, is a novel paradigm that is rapidly gaining ground in the scenario of modern wireless communications. The basic idea of this concept is the pervasive of a variety of things or objects. First thing is pervasive presence, means you have the presence of these radio devices each and everywhere around you, such as radio frequency identification devices, which are of common vision in these days of mall culture. You go to any shop in the mall, you will find the fabrics embedded or tagged with a RFID rate tag. Then sensors, actuators, mobile phones, found everywhere these days, which through a unique addressing schemes, it is part of a research challenge in this domain. Unique addressing schemes, in fact IPv6 has given an answer to this requirement also, are able to interact with each other. So the important part is that these sensors which are available are able to interact with each other and cooperate with their neighbors to reach common goals. So Internet of Things is basically an umbrella which will encompass lot of things, technologies, their coordination, as well as end-to-end applications that will manage the huge amount of data. So big data also comes into picture. Another definition which is quite popular in the realms of IoT is that IoT creates an intelligent invisible network fabric. It's an intelligent invisible network fabric that can be sensed, controlled, as well as programmed. So the IoT enabled products employ embedded technology that allows them to communicate directly or indirectly with each other or the internet. So as you can see that most of the terms which you are visiting or which you are seeing in this definition, in isolation these things are already available. You know, wireless sensor networks, they are available, even commercial products have come in, and as well as internet is also omnipresent these days. But when we merge these two fields, what comes out? That is what is envisaged as IoT. Another perspective definition of IoT is, which I think is more appropriate, that instead of being a single concept, It is an umbrella term used to refer to the global network interconnecting smart objects by means of extended internet technologies. The set of supporting technologies necessary to realize this vision, including the RFID, which I earlier discussed, sensors and actuators. Sensors obviously for the sensing part and actuators for the actuation part. An ensemble of applications and services leveraging such technologies. So the middleware also comes into play. So in a way, IoT covers the hardware, the middleware, as well as the application space. Within the realms of hardware, you have appropriate inputs in RFIDs and WSNs, whereas middleware is more or less service oriented architectures are followed. And at the top there are applications which need to get benefited and inputs from these type of sensors. So the literature suggests various visions for the IoT, Internet of Things, and in a way these visions are thought of, or these directions have been followed into research in three ways. You have two terms in Internet of Things. One is Internet and second is Things. So there are a lot of researchers who have worked on the things aspect of IoT, and they have come up with literature which tries to meet the requirements of things which are involved in the IoT part. For example, sensors, actuators, and all those things. Whereas there is other field or other genre of researchers who have worked on the internet enablement part of the IoT, to come up with algorithms, to come up with middlewares that will enable the internet, that will make internet ready for these type of applications. And thirdly, when you combine these terms, IoT, Internet of Things, so in the combination also, Internet of Things naturally will give you huge perspectives of large, enormous number of sensors integrated, communicating with each other. So lot of issues regarding the integration of the data, pre-processing of the data, managing those volumes, they comes into picture, and these things have been researched or are given in the literature as semantic oriented vision of the Internet of Things. So I will try to cover basically what all is thought of or what all is being researched. These keywords I will give you. If you go through the literature, you will find individual research papers on each and every of these things. So next please. So the as I told you that IoT vision, things oriented vision of IoT has the genesis in the things word. The word literally meaning things. The RFID, which you and me have seen a lot, as I given earlier in the example, in the malls. Commercially, RFIDs are extensively used these days. Here, the end node or the last sensor does not have any battery or power source. They work on the energy harvesting concepts. They take their power from the transceivers, which are high power components in the overall RFID physique. Then lot of work has been done on near field communications and wireless sensors, actuation networks, industrial automation, a lot of wireless heart and all those things. Honeywell products are coming in, which provide you automation. Siemens products are also there. Then another project which if you go through the literature, you will find WISP, wireless identification and sensing platforms. So these platforms also see IoT from the things perspective. Then you have a SPIMES. SPIMES project was very popular. However, it is has not gained much popularity. Where SPIME is an object that can be tracked through space and time throughout the lifetime, and that will be sustainable, enhanceable, and uniquely identified. Then lot of work is going on in the field of smart items. Recently you may have seen a TV ad in which husband and wife are fighting over who will go to the house first, and the reason is that the other wants to enjoy the car AC until the second partner goes to the house, opens the lock and starts the AC and all those things. But the future of IoT does not envisage things like that. It provides for a seamless integration of sensor channels in a way that you are able to remotely control all your settings in the house. So in that sense, smart items are also making inroads, and this realm has also been extensively studied in the IoT literature. The other vision for IoT is internet oriented vision. Here the genesis is in the word internet. So in this realm of literature, what people have tried to do is they have tried to work on the aspects of the internet protocol in a way that makes it ready for use with the sensor networks. So various approaches which has been followed is an IPSO alliance has been formed, IP for Smart Objects Alliance. It's a non-profit organization formed in 2009 by around 28 companies, and basically it's a trend in the technology development. Whatever terms or catchy terms you hear these days, Bluetooth, Wi-Fi, WiMAX, you might be aware that these all are products which have been developed on the certain minimum standards, and they have worked for the standardization of the middle layers of these technologies. And a lot of companies have come in, joined hands, worked on the standards, ratified those standards, so that when they invest in that technology, when they come up with the products, lot of people are aware of that technology in the field. Plus, you have the chance of getting lot of compatible products for your base technology. So it's a trend that companies come in, forms a not-for-profit alliance, and then they pursue a particular technology of common interest because they are part of the entire decision-making process. Then another project is Internet 5, which follows the approach of reducing the complexity of the IP stack. The IP stack to achieve a protocol designed to route IP over anything. So you can configure internet over any device, and they have tried to downsize the IP protocol stack in that manner. Then another approach is Web of Things approach. It is also related to integration of the web with the existing web with the smart sensor networks. And the third vision is semantic oriented vision. So the semantic oriented vision means it envisages that IoT is going to provide the most disruptive level of innovation into the communication technology world. So definitely in the coming days you will have issues regarding representation, storage, interconnection and search, etc. in the IoT, and these are going to be challenging because of the sheer volume of the information which is coming in. So semantic technologies that will help you to refresh this data, help you to rearrange this data, all those things that will give you the semantic oriented approach. And based on these three approaches, authors of this particular paper, Internet of Things, reference 1, has proposed a IoT paradigm. Here you can see a Venn diagram with three visions: things oriented vision covering the RFID, UID, SPIMEs, smart items, near field communication, everyday objects, wireless sensors and actuators, and WISP. There are certain things like connectivity for anything, communication things like projects which fall into the twin domains, and an overall overlapping of all these things, we call it Internet of Things. Internet oriented visions, we cover IPSO alliance, Internet 5, and then Web of Things. And similarly, semantic technologies, data research. Big data is a big thing these days. You have, since in these 20 years with the internet, you have data of around 100 exabytes. It's huge, but think for about some billion to around 50 to 100 billion, what will be the with the sensors generating data at every particular quanta, the volume of data will be there available for processing and all those things. So these technologies work in that domain to make you ready. There are a lot of projects also going on in this direction, like open data center projects are very common these days. So they are all working and making themselves ready for such type of challenges. Now, what are the enabling technologies for IoT? As I already told in the starting that IoT, the basic building blocks of IoT are available already. You have wireless sensor networks, you have Bluetooth radios, you have Wi-Fi, you have WiMAX, you are going to have Google Fiber. In US it is there, which provides you 1000 Mbps speeds also. Plus you are having wireless sensor network technologies like Zigbee. There was Bivri, UWB, some of them have been disbanded, but Zigbee is going good. If you go to the site of Zigbee.org, we will discuss in detail Zigbee if you want. And so in all, we can classify the enabling technologies into two domains. One is the identification, sensing and communication technologies, and the second is the middleware. Middleware, I mean to say, the central part that will provide you the link between the application space and the hardware space. Hardware would be covered by the various sensors, application space would be covered by the top level applications which want to use that data, or those will be used by persons who are transparent to this entire process. So the entire processing part will go into these middleware things. So the identification, sensing and communication part will have RFID tags, wireless sensor networks and RFID sensor networks. It's a new paradigm which merges the WSN with the radio frequency identification. And then in the middleware part, we will have service composition, service management, object abstraction, as well as the trust, privacy and security management. Before going on to this part, I think you all are well aware with the OSI model, Open Systems Interconnection model. We will discuss it a bit and then we will move forward. The OSI model is a basically 7-layer model. Is there any issue? It's a reference model basically, and more or less it's used in almost all communication endeavors. Not strictly adhering to this model, but more or less this model is followed. So at the bottom we have, can you help me? Physical layer. Above physical layer, DLL layer. Then network layer, transport layer, session, presentation and application. Similarly on the other side, there are 7. Now how do communication take place? The data which is required for communication is typically generated here or here at the application part. And how does it physically move? It physically moves in the form of packets from this layer to this layer, and then it reaches the host application. For example, now this is the physical mode of communication, and what we call the interaction between these two layers, interface. Okay. Actually, what happens is every layer appends to this packet a header of its own, which contains some information which is required for the corresponding layer at the other end. So in a way, with the help of that header, these two layers are, or rather these two layers, or for that matter any two layers are communicating. What we call the standards which define the rules and regulations of this communication? Protocol. So interfaces are basically rules and regulations that govern the communication between two unequal layers, and protocols are the rules and regulations which govern the logical communication between two unequal. So similarly, in this case also, you need to have middleware protocols that will enable the IoT communications. So here basically the service oriented architecture is followed, which has these various layers. Service composition that provides services basically to the service management layer. The service management layer provides services to the service management layer provides services to the service composition layer, which interacts with the actual applications. This is basically a protocol stack of the service oriented architecture based IoT middleware. Here you have objects at the bottom, which are actually the sensors. The information from these sensors can be heterogeneous, can be in different forms. For the purpose of applications, you need certain form of abstraction. What is abstraction? Are you aware? Abstraction is basically modifying your data or encapsulating your data in a manner that the necessary information is only passed on to the person to whom you have given that abstracted object. So this abstraction is required to make the upper layers independent of the nitty-gritties or heterogeneity of the sensors. Then the service management layer performs various tasks like discovery of these various objects, status monitoring of various objects, whether they are into the network or they have died down due to some battery issues or other things. Configuration of services, which is initially done when a candidate object joins the network, and similar type of other applications. Above it is the service composition layer. Service composition layer is basically an interface between the actual application and the service management layer. So at this layer, the functionalities for the composition of single services offered by the network object to build specific applications are provided, like repository of all the currently connected service instances, those type of things. Interface between the service management layer as well as the application layer. So most of the IoT based architectures are right now based on service oriented approach. PD next. Pardon? So the various application areas in which IoT is envisaged are huge and vast. We will discuss individual examples when we will discuss the ZigBee part, but still I have enumerated them as transportation and logistics. Here in logistics, it is of great use. Lot of applications are there. Globally, in India, not much is being used. However, these radio taxis and various other things these days you see on the map. You see a taxi is approaching you on the Google map. All those things, they are somewhere output of the IoT omnipresence. Assisted driving, wherein automatic driving facilities are available in certain cars with the help of sensors. Google car, you might have heard a lot. It's a driverless car. Then mobile ticketing, ticketing on the go. You're moving and suddenly your mood comes that I have to go to the movie. You have downloaded an app and you've done it. Even for railways these days, IRCT apps are available. Then environmental monitoring. It's also a very important aspect, and these days with the alarming levels of pollution in the air, you can on the go decide to restrain or empower measures that will, a good application, however it was manual, was odd even scheme in Delhi. So on that sorts, why not we can have cars which shut down automatically if they flaunt the emission. Why the engines are working? We have sensors, it is possible. Then augmented maps, very much you are seeing these days. Ola and all those type of apps, you see a car approaching you, you're also able to diagnose that the driver is going away from you, whereas you should have. These things are reality these days. Then in the healthcare, I think as in our country, these issues are not, these type of applications are not very much popular because healthcare is really in a mess, we know that. But there are a lot of things which are going on. We have online appointment systems in government hospitals in Chandigarh, you might have practiced. That is very comfortable. On that lines, in countries where there is a lot of aging population, for example, Japan. So the population is coming down, the working population is very less. So in those type of environments, these sensor based interpretations or sensor based inputs are very important. You can have track if the elderly people are living alone in a house, so you can have tracking sensors that tracks motion, and if for a particular quanta of time, more than a particular quanta of time, there is no motion, then they can signal an alarm. That is a very common application with wireless sensor networks. Then identification and authentication in the healthcare domain to ensure if someone is claiming for instance insurance and all those things, for those purposes, for forensic science purposes also it can be used. Biometrics can be used. Then data collection. For example, if you have an enabled system in a locality of 100, each house is enabled with a ZigBee network, wherein the coordinator is regularly collecting data, and then through some protocols like 6LoWPAN, that data is aggregated and sent on to the internet to a hospital, which processes that data and then come up with a plan for a particular citizen or a particular group of people. These days you might have heard about Google Trends. That data is also very useful in pinpointing the genesis of the problems. Google flu trend became very popular recently. That gave an idea of where the actually infection is coming from. And then sensing. Naturally, healthcare में sensing का काफी important role है. If you have multitude of sensors which can give you the complete panorama of your health, it will be very good. Then smart environments. Smart environments is also becoming a reality these days. You go to airports, the door opens the moment you go in. In fact, I was reading an article that which visualized how the internet of the future will be. So that depicted that suppose I am going to go to a hotel. So on the basis of my movement tracking through Google or certain other apps, the hotel is able to know at what time I will be in the hotel, in the parking. Based on my prior preferences, they are able to make your settings for the valet, for your luggage and all those things. And by the time you are into the hotel, you get a smart key on your mobile phone which will allow you smooth access or smooth passage to your room, wherein the moment you enter the room which is dormant till now, based on your usage history, it is able to set everything in the room as per your preferences. It will have certain music channel if you are a music lover on the TV. It will have certain setting for the geyser, and I'm not talking something which is like mythological. These things are possible, very much possible these days. Then industrial plants. Lot of wireless sensor networks for pressure monitoring and all those things are already working. Like wireless heart I talked about. It's an automation system, standard from Honeywell. It's proprietary. For open standards you have Zigbee. Then smart museum and gymnasium. These are also applications, and at certain places they are being practiced. And these days, even if you in a smart gym, if you will get basically personalized services. The moment you hang on to some machine, based on your previous history or the sensor which you are bearing, that can be a band, health band, it can set the settings of your speeds or weights of your machines. All those things are quite possible. Then personal and social levels also, IoT are quite useful these days. Recently I got an upgrade from Facebook regarding nearby. So that was able to, on the basis of GPS tracking, that told me who all are all of those friends who are on my friend list, and those who have also subscribed to nearby are able to see at what distance I am from them. So I was one of my best friends' anniversary, which I forgot. I came to know is in Shimla to enjoy the anniversary. So these things are possible these days. Then historical queries, data digging and all those things. Thefts also can be monitored through connected systems. These days a lot of shopkeepers who are alone have to move in from the shop, traditional shops, based on just some employees there. They can track the shop activities in the real time through a camera. Even I am available to you live through YouTube. Then futuristic applications are these you might have lot seen in the science fiction movies. Robot taxi, wherein Google car is one such example. Then city information model. Certain cities are already into the WSN arena. Scandinavia, there is one city called Göteborg in Scandinavia that has entire metering platform based on Zigbee modules. Everything is remotely monitored. Prepaid electricity meters are there. These all things are reality. Then enhanced gaming rooms. Gaming is also a big business these days. In fact, when we talk about IoT, there are two main realms. One is research oriented realm, one is the business oriented realm. It might not be very much useful, but it can have a huge business prospect. So these type of applications are also there. This slide, I don't know, constraints. Basically, these are more of type of WSN constraints, that you have constrained wave bandwidth, radios with very limited amount of memory, highly unreliable because they are battery powered, limited resources in terms of power, memory and CPU processing, because you have to keep the cost low and the form also low. And then extremely high scale networks. So this we can skip. This is basically the architectural panorama of the IoT. You have at the bottom the various hardware infrastructure. Then these days IoT is seen, good number of literature is available on this topic also, that enabling the cloud based platforms for the Internet of Things. One of the most highly cited author works in this field. If you go through the literature, you will find he is one of the most highly cited, 25,000 citations here. And he is an Indian working in Australia. So API cloud services, then you have cloud scale platforms that can be app marketplace, home automation, controller hub requirements, IoT operating systems, and so on. And then at the top you have the things which will use these enabling platform to have intelligent applications that will make your life easy. That will include life safety things, home security things, in a way whatever we discussed in the application slide. So this is basically the architecture of a typical IoT infrastructure. However, I would like to add that this is in the research paradigm only right now. The concrete or finally available architecture that will be able to cater 50 billion devices is under development right now. So at the bottom you have embedded systems and sensors, which is sometimes called smart things network. It includes smart and less smart things, as well as moving things, vehicles, as well as machines. They can be wired as well as wireless. Then above it you have a multi-service edge, which acts like a field area network that will provide the arm's length to your underlying smart or smart things network, and that include technologies like 3G, 4G we are going to see in some days, or some data providers have started giving it, but it is to be launched in big. Then you have Wi-Fi, Ethernet, again trusted thing which is available everywhere, and then program logic control. And above it we have core networking and services, which include the internet protocol as well as MPLS, multi-protocol level switching. Basically level switching is more used in telecommunications, you might all be well aware. And aspects such as quality of service, multicasting, security, network services, mobile packet core, all those things are to be taken into stock in those things. Then at the top you have the application, and the specs which are important in this domain are hosting of those applications as well as management. Now what is required at these levels from the research perspective? So as far as embedded systems or sensors are concerned, you need certain standards, you need certain hardware that works and is able to give you something as output in a reliable manner. So here you have RFIDs, which we have discussed a lot. Then you have 802.15.4. In fact, the entire working group 802.15 of IEEE is on area networks. And within that 802.15.1 is the genesis of, you might all be aware well, Bluetooth. And then you have 15.4, which is for PANs specifically, in the data range of 0.1 to 1 Mbps, or in fact 0.01 to 0.1 Mbps range. In the field area network domain, we need to come out with distributed systems that will be, that should be, or that will be able to manage or cater to the computing as well as storage requirements of the data which is coming from the lower layers, as well as when we talk about the upper layers, the incoming data from the data to service them. At the core networking and services level, we need to have distributed intelligence, and here in cloud computing as well as fog computing. Cloud computing, you are all aware is what is cloud computing? That you have centralized services, you not need to buy individual storage places or individual softwares. You can use paper instance type of model, or in certain cases in storage mostly it's free up to a limit. Basically fog computing, what it does is it tries to bring the capabilities of cloud to a lower level in the domain of field area network, and if possible, maybe possible to the smart things network also. That there are the sensors themselves are able to compute things, process data, and provide services. So obviously there will be an optimization in this, because there is always a trade-off between what you can do and at what cost you can. So you have to maintain a balance between the actual cost that is incurred as well as the capabilities you have. Then at the application level, naturally you will need to have centralized intelligence. And these days lot of work is going on deep learning and machine learning and artificial intelligence type of things. In fact, if you hear from any CEO of a big IT company, on this day he will talk about these things, AI, and you see the TEDx talks or whatever latest ones, you will find deep learning and these things are very important, because once when you are thinking of an automated world, you will need automated intelligence also at that level, which can recently you might have heard that the computer defeated in a very famous Chinese game. Chess and all those has always been uncovered, but there is some Chinese game, I'm missing that name, that till now computer was unable to defeat. But with those deep learning algorithms and AI, finally recently they have defeated humans also, humans in that game also. So here the cloud computing is seen as a solution, or advances in cloud computing is seen as a solution. Now what are the various, here I think in the morning session my previous speaker has talked about ZigBee. So I will give you a quick walkthrough around ZigBee if you are not aware of it, or rather it will be an additional input for you. So ZigBee is basically an established set of specifications for low rate wireless personal area networks. It is a technological standard that has been created for control and sensor networks. It is based on the IEEE 802.15.4 standard. It has been created by the ZigBee Alliance, which extends the upper layers of the stack not defined by 802.15.4. This I have already told you that ZigBee is again a non-profit alliance. Lot of companies came together and they are working on the development of the standard based on the hardware and DLL layer proposed by the IEEE 802.15.4. And they are basically seen as a enabler for IoT, Internet of Things. Here you can see that through a bridge or gateway between the individual ZigBee networks and the IP through certain protocol like 6LoWPAN, you are able to integrate the entire services onto a single storage, and wherein clouds and different type of services are there to cater to your requirements. So this is how the ZigBee sees the world. The name basically came because of the erratic zigzagging pattern of V's between flowers, the way V hovers around a flower. So the genesis of ZigBee name is from there. And as well as all the actors or players in the ZigBee network are also alike the roles played by various types of bees in a beehive. There you have a queen bee, which is one in the beehive. You have supervisor bees, which are many, and then you have worker bees. Similarly, in the ZigBee parlance, you have network components like coordinator, router, and end node. Coordinator is like the queen bee, which is one in the single in a particular network. Then you have multiple supervisor bees or routers, and at the bottom you have the end nodes. Naturally, the coordinator is the most empowered one in the entire setup, whereas the end nodes are most resource starved. They have limited resources. Again, the number of end nodes is huge and they have sensing part on it. Whereas there is one coordinator which controls the network. ZigBee provides support for various types of networking, star as well as tree as well as mesh. So this was basically genesis of ZigBee, why another WPAN standard was required. The requirements were decreasing power consumption. You know, you have a Bluetooth in a mobile phone which you charge every day. Yes, but if you have a switch which works on two AA cells, is used to on off your tube light, but you have to charge it again daily, would you prefer it? Definitely no. What you prefer is, you prefer a line of sight IR based TV remote which have just two cells and it works for years. So a similar thing you require in the WSN network. There, when in the case of TV remote, line of sight is a requirement. You don't want that naturally for a switch and those type of things. It is one-to-one communication. So now in a house, if you have a DVD player, if you have a music player, if you have a television, if you have a air conditioner, kitna remotes ho? The number of remotes is quite high. So with ZigBee type of setting, you can do everything with a single remote, have a profile setting which will set everything accordingly. Next. So these were the basic objectives which required to be decreased: power consumption, production cost, development cost, and bit error rate. And we want to increase the sensitivity of the system, flexibility of the system, security, latency requirements, as well as the range. These are some of the usage scenarios for ZigBee. Industrial and commercial, consumer electronics, toys and games, PCs and peripherals, wireless PCs, personal healthcare, home and building automation, just everything you can imagine for a wireless sensor node, or in general short range communications. This is a typical stack of ZigBee. I think my previous expert has discussed ZigBee Pro stack. So it is the next generation stack of ZigBee. Here the key takeaway is that the lower layers are from 802.15.4 and the upper middle layers up to the API, application programming interface, you have the ZigBee Alliance work done, and at the top the individual vendors develop applications suiting to their products. This is basically the wireless space of 802, wherein you have Wi-Fi which has genesis in 802.11 with data rate of around 10 to 100 Mbps. Then you have Bluetooth with a data rate of 0.1 to 1 Mbps. You might be aware that now Bluetooth is coming in both ranges. You have Bluetooth low energy BLE, which caters to the data and power requirements of ZigBee domain. And then you have Bluetooth high speed, which caters to the requirements and data ranges of Wi-Fi. But these newer versions required that the radio of the Bluetooth be tweaked, and that was not ratified by IEEE. So today what Bluetooth you see is, although a commercial success, it is not ratified by 802.15.1 working group. It is not ratified today because they have tweaked the radio, basic radio of the Bluetooth to cater to the requirements of what is in the domain of Wi-Fi. Similarly, you might have seen that Wi-Fi Direct has come in. Have you used Wi-Fi Direct in your mobile? So that Wi-Fi Direct is a poaching or approach of Wi-Fi Alliance into the domain of ad hoc data transfer into the domain of Bluetooth. So with the Wi-Fi Direct, the image, same image, which takes around 2 to 3 seconds with Bluetooth, you're able to transfer in less than a second. And that feature is quite commonly available these days in the mobile phones. But again, that is not ratified by the IEEE 802.11 working group. So this was the requirement why the need for ZigBee was seen. There was no standard which was catering the range of 0.01 to 0.1 Mbps data rate in the wireless PAN space. And ZigBee tries, or it uniquely fills a gap for low data rate applications. Again, ZigBee operate in the ISM band, industrial, scientific and medical band. So in India, the frequency which is available for ZigBee is 2.4 GHz. Because these other frequencies 868 and 915 are quite costly airwaves in our country. GSM works in this particular wavelength. However, there is one channel 868 MHz is available in Europe and 915 MHz is available in North America with 10 channels. There are certain other bands which are available in China, but universally 2.4 GHz is all anyway available. So what does ZigBee do? It is designed for wireless controls and sensors. It operates in the PAN and device to device networks. The connectivity between, it provides the connectivity between small packet devices and it is basically intended for control of lights, switches, thermostats and applications, whatever is we think of a wireless sensor network. Architecture, I think, so here is the basic architecture of ZigBee network. You have a 64-bit addressing scheme, so you can have around 65,000 client nodes. There are 27 channels in 3 bands. The data rate is typically 250 kbps, and ZigBee is basically optimized for time critical applications and power management. It provides for full mesh networking support. Then you have various types of node in the ZigBee network. There is only one in the entire network which we call ZigBee coordinator, and in the 802.15.4 paradigm it is called full function device, FFD. It is only one in the network. Naturally, you start the coordinator node at first. It stores the information about the network. All devices communicate with the ZigBee coordinator. It has a routing functionality to route the data from one end node to other end node, and then it also acts as a bridge to other networks. You can have IP bridging or tunneling other things at this particular coordinator only. This can't be done at other nodes. So in a way, it is a master node in the WS. Then you have ZigBee router. So here you can see that I have written FFD for in the 802.15.4 domain only. Yes, because in 802.15.4 they have defined only 2 types of node, RFD and FFD. So a router is also a full function device as far as 15.4 is concerned. Naturally, it is an optional component for extending your network and other things. It routes between nodes, which will be definitely child nodes. It extends the network coverage. You might have done it practically. And manages the local address allocation and deallocation. By this I mean the allocation and deallocation of the address nodes which are child nodes of that particular router. Then you have the ZigBee end devices, which are like akin working bees, or in the 802.15.4 parlance they are called RFDs, reduced function devices. Naturally, they are optimized for low power consumptions, low latency requirements. They are quite cheap and small in form and factor, and normally houses the various sensors onto them, and the sensors would be deployed here. Now again, you can have various types of traffic on the ZigBee network. The one case is the data is periodic, so the application dictates the rate when the data will come on. Second is that data is intermittent. Periodic cases are there when you have certain system which is performing temperature logging task or rain logging task, like that type of application. Then second, the data is intermittent. By intermittent I mean it can come at any time. For example, what type of application you can think from such a thing? Can you name any application? Fire sensors, pressure sensors, seismic monitoring sensors. So even earthquake early warning is a very big research topic. and some people at CSIO are also working in that domain. Recently they have been successful in very basic agreements for a very good agency, but as far as definitely they can go on to this type of sensors also. However, they are basically, since the distances and all those things are huge now, so they need some sort of triangulation type of application, wherein the distance between the triangle sensors is quite large. So they use different type of seismic sensors. I don't know whether they are into WSN domain or not. Then the third case that the data is repetitive. Repetitive means it is fixed at a prior rate, and if at all there are 10 sensors, data will come in at particular time slots from an individual sensor. So in this case we have certain mechanisms like guaranteed time slots, in which in a certain wake up period of the network, particular slots are available or fixed for a particular sensor to send data. In case of periodic, there will be certain contention things. We will discuss it later. Then the various traffic modes which are available in ZigBee. One is the beacon mode. In this mode, what happens is that a beacon is sent periodically, and once the beacon is sent, the coordinator and end devices go to sleep. This is typically used in cases where even the coordinator is battery powered. The energy consumption is lowest, but naturally in case of beacon mode, you need to have precise synchronization. Timing is a very important parameter, because the beacon which goes from coordinator to all the network devices will have information regarding the next backup time of the entire network. And if timing is not maintained, the particular node, or even for that matter coordinator, can miss the duration in which it will have to wake up, and so data failure will happen. And then you can also have an optional acknowledgement mechanism in this particular setting. You can see initially red beacon comes in, then depending on the information that is contained in the beacon, there is a beacon extension period. After that, once all the network devices are wake up, there is a contention period. In this contention period, as you can see, there are various slots in the contention period, skin colored contention period also. Within each slot, every node or coordinator can communicate following CSMA CA: carrier sense, multiple access, collision avoidance. It will sense the channel. If it is free, it will dump the data. Otherwise, it will wait for the time period when the channel is free. Then after that, the green colored GTS period you see. So this guaranteed time slot period is for periodic data. Here CSMA CA is not applied. It is तो तुम लोग को भी आ रही है ना, मुकेश को सबसे ज्यादा आ रही है. Ready? Ready? अच्छा ये भी लोकल ही है कि ये ऑनलाइन
ऑनलाइन वहाँ से हो रहा है ना ब्रॉडकास्ट वाला एंड फाइनल में
फाइनल के अंदर embedded system for IoT is compulsory mitigate that.
अब देख लीजिए सर F5 प्रेस कर दीजिए
So we had a tea break due to power failure. So we were discussing about the beacon mode communication, and as I told you that there are provisions for guaranteed time slot as well as contention free packet. Then the other mode is non-beacon, in which naturally you need to have a waked up controller all the time. So in these type of applications, the power is basically asymmetric. The coordinator is battery powered or mains powered, and the with lot of power surplus, and whereas the end nodes are as usual power starved. So here, whenever a network device has some data to communicate, it sends on to the channel, and the coordinator or router are awake to gather that particular data. And a optional acknowledgement can be taken. I think you are well aware with this mesh topology, and we can skip in mesh. You can have inter-router communication basically, or at the same level of hierarchy. This is a good example to depict mesh. Then this is a typical stack of a Zigbee stack architecture, wherein you have the physical radio and medium access layer defined by 802.15.4, and then at the top you have a network layer, which is typically an end-to-end layer which provides network organization, route discovery, and message relaying type of functionalities. Naturally, up to medium access layer you are at the hop to hop level, and you have security layer which performs the security functions, and then you have a ZDO, Zigbee device object. Basically the identifiers which are assigned to various applications in Zigbee domain are called endpoints. You can have at a time on a particular node 256 endpoints. So it's basically a 8-bit mechanism. So on a particular node, endpoint address 0 is assigned to the Zigbee device object, and you have from 1 to 240 you can have devices or sensors onto it or applications onto it, and then 241 to 254 are reserved for future use, and 255 is the endpoint address. 255 is assigned for broadcast. The ZDO performs a task like device management, discovery, as well as a service discovery. By service I mean, for example, if you have a switch, Zigbee enabled switch and a Zigbee enabled bulb. Now if you want to toggle that particular bulb with that switch, there will be some sort of binding between the application, toggling application on the switch node and the toggling application on the bulb node, and that binding will be based on the services which are offered and which are given by these nodes. That binding table is also maintained at the application support layer. So once bound, you can have various type of relation, that they can be one-to-one, they can be one-to-many, or rather many-to-one also. Then finally at the top you have the application, which is responsible for initiation and joining of network, for management of the network, determination of device relationships, as well as send and receive messages. For Zigbee, I would recommend you a tutorial on the site of Zenic. If you just key in on the Google Zigbee tutorial, you will have a 6-module tutorial which is quite simple and will give you a broad idea of what you can achieve with Zigbee. Okay, and then you have various kits. One I think you have right now, that EK10 kit, NXP one. Basically it was Zenic. So Zenic was taken over by NXP. These days NXP comes in with EK50 kit, which also have on-chip GPS and support for IP integration. All those things are also in that. So it is basically, this one is only up to WS, and you need to have additional hardware for those things. Now implementation of Zigbee, I think if time permits we can move fast in this domain. So in the 2400 megahertz band, which is 2.4 gigahertz band, at the physical level we have 4 bits per symbol. The spread spectrum technique which is followed here is DSSS. Are you aware about DSSS? It is contrasted with FSH, frequency hopping scheme of Bluetooth. Then you have quad force shift keying modulation in this case, and sine half wave impulses are generated. These other aspects are of not much use to us because these wavelengths are anyway not available in India. These are the functionalities of various layers. They can be extended and interpolated into the requirements of WSN. As far as broadly concerned, They are more or less like as defined in the OSI layer. Then channel access specification, I have discussed various types. It can be weaken, it can be non-weaken mode. Then super frame is basically a control frame of the MAC layer which is generated to control or to establish the initial links and all those. Then you can have slotted or unslotted CSMA CA. Slotted is GTS mechanism, unslotted is that contention period. MAC layer basically performs these tasks at the lower level: transfer handling, and then frame security at the frame level. Now you are well aware with the networks. Up to MAC layer we are at a 1 hop distance. Only 1 hop connections are established, and naturally if you want to establish routes from multi-hop locations to a distant location, then you need to have some sort of routing naturally. So for that routing, those tasks are performed by the network layer. Here also the algorithm basically which is followed is AODV, ad hoc on demand vector. So these are various functions of the network layer. Distributed address assignment. Herein what is done is that I've told you that you have a long address of 64 bits, whereas we have a short address of 16 bits. So the 16-bit network space is divided into the various child routers. Then the child routers further divide this space again for their further children. And the net distributed address assignment decisions are taken depending on your algorithm which you have chosen, either on the physical hardware or you can use simulators also. So normal parameters which are used is maximum child count per parent, maximum child routers per parent, and then you have maximum network depth. We can have a visual example. For example, in this case we have maximum child count 2 and the network depth to be 2, and suppose a new node in question comes in to join the network. If it approaches to join the router 4, naturally it violates our CM/RM equal to 2 rule, LM equal to 2 rule. So it is denied a connection, and it naturally, if it is in the range, it gets attached to router 1. Then route cost estimation. Here the metric is goodness of the routes. Generally we use parameters like power quality indicator of the nodes on the route and other things. Then route discovery is another task. It is based on AODV algorithm, which you send certain route request packets and wait for the receipt of return paths. And the packet which comes from the shortest path, naturally you choose it as a preferred path and you establish it in the routing table. So here the packet is coming back from 3. It is the shortest path and it is an entry is created into the routing table at the network layer. Then again, if you have a routing table, you need to have route maintenance. So track failed deliveries to neighbors, initiate route repair when threshold has reached. There are certain thresholds for the data loss also, क्योंकि there are cases of data loss, वैसे भी कुछ एक अच्छा खासा rate है data loss. Then you have the application support layer. This application support layer, like the middleware which we have discussed, is more or less an interface or standing between the network layer, which more deals with the hardware, and the actual applications. So as I've told you that at the top there are applications, you at a single node you can have up to 240 application endpoints, which are called endpoints. And ZigBee device object is assigned endpoint address 0. These endpoints interact with the lower parts of the network through application support layer, and the packet is basically called service access protocol, SAPs packet. Sorry. So these are basically the tasks performed by the application support layer. Interface to the network layer, data transmission, binding of various devices, and finally discovery of the devices also. And at the top you have the application objects, which are actual applications which are running on a end node or controller. Now, like in any programming language, you have certain data types. So here also individual data types are called attributes, and a group of data attributes, which in general C parlance we call structures or unions. Here you call them clusters. Then you have individual specific device descriptors, which describes a particular device. Who I am an end node, my MAC address is this, my endpoint address is this, and then within that endpoint I am related to this particular cluster. And when binding is done, that binding basically incorporates this endpoint address plus cluster address plus MAC address on one part and on the second part, and they are joined, and in that manner the data flows and actual implications are felt. I think ZigBee device object we have discussed. It is it defines the role of devices within the network. Naturally, whenever a coordinator node is started, it defines the role of devices within the network. Then it initializes the application support layer, network layer, and the security services specification. Further, it offers services like device, service discovery, binding, as well as security management. And then it also maintains the binding table. These are basically, this slide relates to the certification part basically. So if some vendor wants to develop a ZigBee application and he confirms to the MAC physical layer as well as the ZigBee stack, which is in a way middleware to him. So if his product is compliant with those two things, it ensures that his product will be interoperable with any other product which is ZigBee compliant. And this type of product delivery is called ZigBee compliant product. Again, ZigBee itself works on lot of standards, and it comes up with several public profiles, which provides you a vertical slice through the entire protocol space. Even the application APIs are defined by ZigBee Align. So in that case, the product is called ZigBee logo product. And like you see the Bluetooth logo on any particular device, similarly, if you are using a ZigBee public profile, your product can have that type of ZigBee logo. A typical example of a application profile you can see here. As I've talked about, a switch and a thermostat are connected. On the switch, there is an application cluster which has 4 options. 0 is off, 1 is on, 2 is scene 1. Scene 1 means that particular switch is binded with whatsoever devices, lighting, geyser, television, music, kitchen, they will have a particular output. It's a sort of one-to-many relationship. And then scene 2. So for example, if it's in the morning, what do you want? You don't want lights in the house. If it's a chilly morning, you want certain heating things in the house. And similarly, if it's evening, you want all the lights blown up. If it's windy, if you have wind sensors outside, you don't want your windows pans, automatic windows to open. And if it is not windy, you want some fresh air. Similarly, another cluster is fan off, on, temperature set and time set. Now application profiles define what messages are sent over the air for a given application. So what an application profile is defining? It is defining what messages are sent over the air for a given application. Devices with the same application profiles interoperate end to end. If two devices have the same application profile, then only they can interact. Naturally, then only they will be able to bind. ZigBee publishes a set of public profiles, but vendors may create manufacturer specific ones as well. So manufacturers are free to create their own application profiles. Now ZigBee Alliance also does certification of ZigBee products. So the basic objective of certification is to ensure that the applications does not interfere with other ZigBee networks. It allows a vendor to build specialized products with a ZigBee compliant platform. Certification testing ensures that the product does not harm other ZigBee networks. And the manufacturer specific applications are not intended to interoperate at the application layer. This is what I have told, that if it's a manufacturer specific profile, then it is not intended that it will interoperate at the application layer level. However, they have to interoperate at the stack level, ZigBee stack level. It allows product vendors to use ZigBee language and logos on their product. Now, the ones with use the ZigBee public profiles. If you go to the website of ZigBee Alliance, you will find around 20 to 25 public profiles. Home automation, that type of lot of public profiles are available. Yes, energy metering. Besides that, lighting, HVAC control, lot of profiles are there. Car, I think recently car automation ones also have come. Yes, so that will allow you to have a product which will interoperate with every ZigBee product which is with that public profile. So it guarantees the interoperability between products all running the same public application profile. Product vendors may add additional features to the public profile. This is how Linux or for instance any open source platform works. It allows vendors to use ZigBee language and logo on their products. Now I think application scenarios we have already discussed. So it's a different view. You might find the colors attractive. So security, building automation. Many a times we find that the street lights are on. Naturally, mostly during this period of transition, we will see that street lights are either off up to a bit late time, or when the reverse cycle begins, they are on in the morning. So those things can be managed very well with the ZigBee type of things. Then you have industrial control applications, mobile commerce type of applications. This definitely needs some telecommunication intervention. Then home control, including security with burglar alarm sensors and all those things, fire sensors, water overflow sensors, air conditioning, lightning control, and access control. This you can see a typical house in the top picture, where a Zigbee coordinator is there and various Zigbee nodes are there, which performs entertainment controlling, light controlling, high voltage monitoring and control, automatic window opening closing. Then your motion detectors, that for elderly type of if the house is alone with a single elderly person who can sense the motion. And then smoke detectors for firefighting type of applications. Then you can have sensors attached with the sprinklers also. And in case of industrial scenario also, you can see you have environmental monitoring sensors, high voltage AC monitoring and control sensors, wall positioning sensors, then remote tank level monitoring and control, machinery control and status report. These all things are functional. As far as WSNs are concerned, lot of sensing applications are functional, and that is why when we were talking about IoT, I was telling that the enabling things are there, but we are not ready for that mass 50 billion plus type of sensors. And lot of work needs to be done on those things. Another good picture for home automation. This typical example, I already told you that you don't need to have multiplicity of sensors, remotes. You can have a single remote with some certain scenario settings, and that will perform all the tasks. Inpatient home monitoring. Here we are up to the WSN level. When we integrate it with the IP and all those things, it comes in the domain of IoT. So patients receive better care at reduced cost with more freedom and comfort. Patients can remain in their home, but these things are, I think, in our country right now, even our best institutes are so crowded that, but still there are certain pockets. If you go to military hospitals, they are well equipped. Then if you go to certain other trust hospitals or private hospitals, in a way they are equipped, but then they have a case with talent. In those messy hospitals, the type of talent you get is better naturally, and that is why they are mess. Lot of rush or crowd is there. Yes, yes, yes. Yes, and as far as automation is concerned, we think I think with the growing population or growing medical, this Skill India initiative, if at all we can create lot of primary health professionals only who can look the patients at a primary level, because lot of deaths occur just because of, in a road accident mostly death occurs because of bleeding. By the time you reach the hospital, your blood is drained. So those things, you can have smart dresses. For example, why can't we have RFID dresses in case of high altitude things, like that instance yesterday Siachen one. Those RFID tags would be anyway passive, but that needs to be sent, that if they can penetrate those 25 feet of, for sensing, you don't need then sniffer dogs, no? You can have sensors for those type of applications also. Then allows monitoring of elderly family members, sense movement or usage patterns in home, turn lights on when they get out of bed, notify via mobile when anomalies occur, a message is generated, and wireless panic buttons for falls or other problems. Then it can also be used in the hospital care, in ICUs and all those type of settings. are allowed greater movement because they are connected with sensors and real-time monitoring is going on, and reduced staff to patient ratio. Commercial lighting control, it has lot of uses because a lot of power is wasted or means misused in this case also. So wireless lighting controls, naturally the management would be quite easy, but those sensors need to be again quite rugged because they are usually positioned in a hostile environment, and that behavioral feasibility aspect also needs to be seen. Recently we heard the news that a new swanky train has started from Delhi to Banaras, and within a week what happened? Lot of taps are missing, those readiness also are important. However, that can be researched in when we prepare some article for the purpose of interaction of IoT with behavioral aspects. That is again a very good domain. Temporal studies on those things can be performed. Then light switches, sensors anywhere, customizable lighting schemes. Depending on, you can have ambient sensors, which on the basis of can tweak the wattage requirement of the light source. Quantifiable energy sources, opportunities in residential, light, commercial things. Then you can have extendable networks, wherein you will have integration of the lighting network with other building control solutions. For example, if certain catastrophic is happening, there is certain leakage of current into the water system. So if those things are integrated, immediate decisions can be taken. This is a typical by this picture I try to show the ease with which maintenance can be done. So design wireless lighting, it simplifies the lighting control system design, because in this case you don't need to have the wire between the switch and the actual point. That requirement, you will have directly power source at the, so they are far more safe. Usually the power shock is received from the switch part. If there is no direct power at the switch, it's quite safe. Installation would be easier because you don't need to have interconnected wiring between the light source and the switch. And then simplicity of commissioning. Operation, naturally, if you have a scenario based control, right now even at our places we see that you have a single switch for 10 lights. Even if you need or don't need, you have to put it on. So with that scenario based approach, you can have intelligent lighting which will save power and money also. And then management is quite easy. You can have scenario based approaches that will ensure that those daylight timing mismatches does not occur due to human error. Then hotels already we have seen that they have a key based system. A switch is associated with the key. The moment you pull it up, lights are on, but that is first of all manual. That is basically in the old setting. But with this thing, you can have more intelligent control over various things. Centralized HVAC management allow hotel operator to ensure empty rooms are not cooled. Easy to retrofit. Battery operated thermostats, occupancy detectors, and humidity stats can be placed for convenience. Personalized room settings at check-in. I was talking of that example. I think we miss in between. So the moment you reach the hotel, Your valet will know whether you like that your personal or the hand baggage is taken up or not. Once you reach the room, everything is established as per your requirement. Then he knows when you plan to leave with certain scheduling apps of yours. Before you're leaving, everything is ready at the reception for you, and you leave the hotel in a happy mood. Then advanced metering platforms with Zigbee. This I was telling the example of Gutenberg. Actually, the entire city is connected with Zigbee nodes and repeaters. Now this is where IoT comes into play. Okay. You wish to use mobile headset as a Zigbee gateway. So in a mobile phone, a Zigbee enabled SIM, the personal token can play the gateway role, and through a network operator infrastructure, data can be sent to the service center. These days refrigerators are coming with such sensors. LG refrigerator, if you have, they are coming with such sensors that if you have some problem with that particular refrigerator, you need to have certain settings through which you can send your data to the service center also. This is a bit old list. These days lot of products are available. Philips is even Philips is coming up with a commercial product. I think Deepak might have discussed about that. Yes. So this is Gutenberg. It's in Scandinavia. Basically telecommunications, the hub is in these 4 countries, Baltic nations, Finland, Scandinavia, whatever big names you might hear, Motorola और Siemens, वो जितना भी IN वाला कंपनीज है, इंटेलिजेंट नेटवर्क वाला, सारा बाल्टिक नेशंस को ही बिलोंग करती, because they are very strong in telecommunications. So again, Gothenburg is the Zigbee city which has 5 lakh citizens, and there are around 2,60,000 meters installed, approximately 8,000 concentrators, and there are around 3,000 GPRS meters also. So they have power reading ratings and water ratings, all are distance mode. Now this is a particular which I think we discussed in the hotel context, but again it can also change your home also. So meet and greet means automatic keying. The moment you enter, the door automatically opens up with sensible sensors. These sensors know your scenario, know your usage pattern, which are set definitely predefinedly by you. And then you have a climate control, safer space, no hazard lighting, and then finally smart sprinkler, which does required temperature settings automatically. These are the references, and we will go back to the. So what are the various challenges in IoT? These are the research challenges. I've searched through the literature, and basically 4 limbs are there for research in the IoT space. One is in computing, communication, and identification at the lowest level. Then you have the requirements for distributed systems. Then at the top of it, you have requirements for distributed intelligence. And parallelly with all these things, you want secure systems. So security is another very important aspect. So as we are running out of time, we will discuss In short, all these research challenges and some of the questions which, if you wish to pursue your research in this domain, it will be quite helpful, I think. So in the domain of computing, communication and identification technologies, the various questions are: how to reconcile the scaling laws derived in the context of in-network computing and ad hoc communications with a practically viable IoT architecture. Means whatever optimizations you have done for the need or for the want of your isolated WSN or your isolated RFID network, how you will scale up things for a IoT vision wherein everything is interconnected through a IP based paradigm. So it is an open question. Then an architecture supporting low power, low cost and yet fully networked and integrated devices fully compatible with the standard communication technologies. How will you come up with such an architecture? Right now, whatever SOA based architecture is proposed, that doesn't completely fulfill these requirements. And then naturally, you have to deal with heterogeneity. Vast variety of sensors, vast variety of temporal settings, and you have to make intelligent decisions with these interconnected huge variety of sensors, 50 billion. Second is at the level of distributed systems technology. Here today with just internet we have such a huge data that our big data algorithms are finding their limits. Now consider when 10x times the sensors are sending that data and the type of storage and management requirements you are going to have. So how to control the huge amount of data injected into the network from the environment? How to meet the requirement to replace, repair, reprogram faulty, possibly embedded devices and to design a system natively robust to the failures of single node or group thereof. So it may be the case that the devices are embedded, the radios are embedded. If there is some hardware failure, how you will manage the replacement or repair of those things? Because with miniaturization of hardware, repair these days is more or less not preferred by any company or any organization. Then the possibility to address an object and a network node in a seamless fashion. That you are at the fourth level, at the application level, and then how seamlessly and how will you have the transparency between the distributed systems and distributed intelligence to the lower level that you are easily able to control those sensors. It will be a big mess. It's quite deep technical issue and requires a global scale standardization effort. Then in the realm of distributed intelligence, these are basically semantic aspects. So how to develop suitable, scalable service delivery platforms that permits multiple services from a huge variety of sensors, and those sensors may be possibly quite restricted in the resources. Then the reference models available have a clear gap regarding support to the composition of IoT based services. Those reference model, middleware reference model right now are not able to cope up with the volume of sensors which is envisaged. Finally, challenges in the security domain. They can be broadly quantified, classified in three things: confidentiality, then privacy, and finally trust. If I'm giving something, these days a lot of e-commerce is happening, but at the same time lot of frauds are also taking place. So how can I trust that my health information is not misused by someone, if at all it is sent on to the data? So that trust gap, and naturally what I think behavioral aspects also come into it. If you can see, if you go into the society, you will see that most of the people who are 50 plus, they don't even use ATMs. They prefer going to the branch. They still prefer the passbooks. People of our generation, 30 to 50 years, they have started believing in internet banking, but they are not using mobile banking. Okay. The newer generation, they will ruthlessly use mobile banking, but whenever they become rigid towards technology, a age comes, then they will also be adamant to adapt to the newer things. Because of that, these are the issues basically. They have doubt regarding trust issues, because it may be confidential, it may be private, but at times I don't have trust that I am giving, whether I should give or not give. So the various questions in this domain are data stream access control, how to manage it, identify the management system, preserving confidentiality, and then aggregation techniques. In the privacy domain, we have to come up with a general model for privacy, because hacking and all those things will definitely come into play. Enforcement mechanisms for privacy, they needs to be developed, are not very mature right now. Then governance of data is also aspect. And in the trust part, mechanisms that will ensure the trustworthiness. Right now in person to person communication, how do we believe? Just by our prior experience that this person is trustworthy or not trustworthy. So similarly, you will need to have certain systems, mechanisms or applications that will ensure that the trust is maintained. And then object identity management systems, all those things, lot of work needs to be done, which you can do. Crowd management is also a good application of IoT. Now, these are some of the hardware resources which are readily available, and if there are students who want to work onto their MTech or PhD projects, they can look into these things. So Raspberry Pi boards are there, which provide you a lot of interfaces. They are single board computer sort of things. They have a lot of sensors embedded onto the board, and you can integrate them with your readily integrate with your TV or your other output devices. Most of these are open source, so their source code is available with you to manipulate it, play with it, and come up with newer solutions. And naturally, if you work on them, Linux is an open source system, but you see how many commercial companies are working on that open source system. Eclipse is an open source IDE, but even best of the best RTOS are coming on that platform. Then another is Microsoft IoT Pack for Raspberry Pi. You have Arduino No. These days it is quite popular with the students. Then BeagleBone Black for large amount of wired connectivity. Then you have that Zigbee kits. We have one at CSIO, which you might have worked on. So they also have a lot of functionalities, GPIO facilities, UARTs, all those things. Then from ARM also you have a Ethernet IoT starter kit. You can work with this also. Vast mode platform for industrial environments. It is also available with onboard open source wireless platform with focus on low power consumption. And the battery life you see is 1 to 5 years. Now, globally, IoT has got lot of attention. Recently, some days ago, you might have heard Digital India program was launched. So in that also, IoT has been given a special impetus. And the government of India is going to set up a center of excellence for IoT. It is a combined initiative of Department of Electronics and IT, ERNet and NASCOM. They are coming up with a center for excellence in IoT with objectives to, as you can read out, to create innovative applications and domain capability across verticals. Telemedicine में आज की डेट में हमारा काम बहुत हो रहा है वैसे, हालांकि it is at research level more. Smart city project, smart health project, smart manufacturing, smart agriculture, all those type of things. You see Israel. Precision agriculture, they do lot of work. They don't have water, they don't have greenery, still they are able to produce their requirements based on the precision agriculture and smart agriculture. Provide an ecosystem for innovation to thrive and embrace entrepreneurship, to energize research mindsets. So they will provide some naturally facilities for research in this domain as well as probably funding for this research domain. To position India as a provider of end-to-end solution in the engineering space and to provide environment for creation, testing and also for validation and incubation. They might come up with certain incubation centers which will work on or provide for commercialization of the technologies developed at those centers. So I would like to conclude that IoT has the potential to add a new and disruptive dimension to the internet by enabling the communication with and among smart objects. The internet of future is likely to be dramatically different from today, and IoT has definitely a role to play. The current technologies make the IoT concept feasible. It's like object orientation with C++. But do not fit well with the scalability and efficiency requirements of the future. The impetus on networking and communication research for IoT would be quite high, and the possibility of a seamlessly merging the real and virtual world, what we have been seeing in the scientific movies. So those things, through the massive deployment of embedded devices, opens up new exciting directions for both research and business, and that will include not only dimensions relating to feasibility of IoT, also the implementation aspects of the IoT. In the defense also they have lot of applications. Border management, strategic border management, those all things also require lot of technology interventions. So these are my references. I basically based this talk more on a IoT papers from in various good journals, and if you want to share them, I can share. Thank you. And if we have time, we can continue with that, madam. Oh. So, are there any queries or? Yes. Yes, PVP Siddhartha.
Good evening, sir.
Good evening, ma'am.
A wonderful session delivered by you, sir.
Thank you.
Uh, and at the same time, we are not having any doubts regarding IoTs. Why? Because you enriched the knowledge regarding IoTs, sir.
Yes, yes. Thank you.
Thank you, sir.
So I can hope that all the participants have a wonderful experience from this session. They have learned a lot from his vast experience and knowledge about this IoTs, right? So thank you, sir, for sharing your precious time with us. So tomorrow again we will have session in the morning, and that will be on ARM processors, that is advanced risk machines, and we will start by 9:30 tomorrow. Thank you.